Network Protocols and Services. About this module. Welcome to the Network Protocols and Services module. The digital world runs on networks powered by intricate technologies working in unison. In this module, you'll learn how ports, protocols, and services enable devices to communicate. You'll explore local area network, LAN, and wide area network, WAN, technologies, Internet protocols, IP addressing, and network optimization. You'll gain the knowledge you need to describe how to configure and troubleshoot networks for optimal performance. Learning objectives. After completing this module, you should be able to explain the role of ports, protocols, and services and their process of working together in network communication. Explain the purpose and functions of Internet protocols. Describe the characteristics and application of LAN technologies. Follow the process for configuring and managing IP addressing. Describe the characteristics and application of WAN technologies. Choose a common optimization technique for a WAN technology given a scenario. Describe Internet protocols that power Internet-based communication tools and email. Analyze methods to troubleshoot Internet communication tools and Internet protocols given a scenario. Explain the role of different network services that support the functionality of the Internet. Determine the network service to troubleshoot given a scenario. About this lesson, Introduction to Ports, Protocols, and Services. Have you ever wondered how you can send a message to a friend halfway across the world and, within seconds, they receive it? This is the magic of network communication, where protocols and services work to ensure that your messages, emails, and data traverse the digital highways with precision and speed. Let's take a look behind the scenes at the Internet's infrastructure. In this lesson, you'll learn about the key elements of network communication, ports, protocols, and services. These components work together to ensure that data travels securely and efficiently within networks. You'll also gain insights into the characteristics of LAN and WAN protocols, and their roles in local and wide area networks. Finally, you'll learn about Internet protocols that work across networks. An overview of ports, protocols, and services. Watch the video about an overview of network services, protocols, and ports. Afterward, you'll answer a question about what you learned. Page 1 of 2. Video transcript. Network services, protocols, and ports. Meet Emily. She's ready to review the documentation on some of the networking hardware that her company, Opera Enet, uses. She types in a web address, and instantaneously a web page appears. From the moment Emily presses enter to the moment the web page loads, network technologies, including services, protocols, and ports, are at work to ensure seamless communication. Let's travel alongside Emily's data, from the moment she types the Uniform Resource Locator, or URL, to the moment the web page displays to learn about these critical network technologies. Emily begins by typing in a URL. The first stop is the Domain Name System or DNS. The DNS is a service that translates the web address into an IP address. Services are specialized software that developers build to perform a specific function on a network. In this case, the DNS service translates the URL into an IP address to direct requests from requester to server. Once the browser finds the web server, it can establish a connection to send and receive data. But before that communication happens, our data must adhere to specific protocols. Protocols are a set of rules that determine how data is transmitted and received over the Internet. When Emily types in the URL, she starts it with HTTPS. HTTP and HTTPS are protocol identifiers. It tells the network that it must use the Hypertext Transfer Protocol Secure or the HTTPS protocol. The HTTPS protocol is a communication protocol that ensures data privacy using encryption. To establish a connection with the server, the browser uses the Transmission Control Protocol and the Internet Protocol, or TCP/IP. TCP is a protocol that establishes a connection between devices, then manages how data packets are created, sent, received, and arranged when they arrive. TCP establishes the method of connecting and uses the IP's addressing to then route traffic. The establishment of a TCP connection uses a three-way handshake. First, the browser, or client, signals its intent to connect, providing a unique number for message tracking. Then, the server acknowledges this and shares its own unique number, indicating readiness. And lastly, the client then confirms receipt of the server's number, finalizing the connection setup. To create security in HTTPS, the Transport Layer Security Protocol, or TLS, is used. TLS is a security protocol that encrypts the data exchanged between a browser and the server. This handshake must occur to establish the final connection between the two devices. Once a secure connection is fully established, the browser requests the page from the web server using HTTPS. Because it's using HTTPS, the protocol requires the browser to connect to the server at port 443. Page 2 of 2. Ports are a virtual gate that allows a specific type of network traffic to enter or exit a computer or device. They organize data transmissions, directing them to the right application or service on a device. The server monitors port 443, processes requests detected there, and sends a response back to the browser. When the browser receives the response, the browser renders the web page so Emily can see the page she requested. As you can see, services, protocols, and ports work together to facilitate communication on a network. Whether Emily is visiting a website, or sending an email, these network technologies ensure that data can be sent and received quickly and securely. The role of ports, protocols, and services in network communication. Modern air travel is not only a feat of engineering but also a complex, major logistical accomplishment. Getting passengers and their belongings from one place to another safely and quickly requires hundreds of technologies, people working together, and everything working properly. When air travel works well, the traveler doesn't notice most of the complexity. Like travelers used to well-functioning air travel, people who have been around computer technology for most of their lives can take networks for granted. If you send a text message or a post to your favorite social media site, you expect that message or post to reach its destination. Getting data from a source to a destination requires dozens of different pieces of technology, doing various jobs, working together securely and without errors. 3 technologies that are central to networks are the following: ports, protocols, services. Each of these technologies works together to get data from the source to its destination. IT support technicians must understand these technologies when troubleshooting network issues and optimizing network performance. Understanding ports, protocols, and services is also vital for providing support for communication and collaboration applications, as these technologies are a large part of the functionality of email and messaging applications. Select each tab to learn more about these technologies and their role in networking. Ports. Different types of data enter and exit through their respective ports, making it easy to sort and direct network traffic. These are like designated gates through which data flows. Example, when you browse a website, your computer communicates through port 80 if it's not a secure site and through port 443 if it's a secure site. Protocols. Networking protocols define the procedures and format a device must follow to make sense of the incoming data and know what actions to take. Think of these as the rulebook for how devices on a network should communicate with each other. Example, Transmission Control Protocol/Internet Protocol, TCP/IP, is a protocol that manages the overall transmission of data over the Internet. Hypertext Transfer Protocol, HTTP, is another protocol used for web browsing. Services. Network services are specialized software developers build to perform a specific function on a network. They rely on particular ports and obey specific protocols to do their jobs. Example, a web server is a service that delivers web pages to the browser. An email server takes care of sending, receiving, and storing emails. Ports, protocols, and services working together. A map showing air traffic routes between cities across the world. Imagine all busy international airports as a network. Together, ports, protocols, and services coordinate to ensure that data travels safely and efficiently from its point of origin to its destination. Select each card to learn more about how ports, protocols, and services work together. Ports act like the individual gates where airplanes land and take off. Just as each gate is designated for a specific route and type of plane, ports ensure that the right data gets on the right plane to get to the right destination. Protocols are like the established set of air traffic control rules and procedures that pilots and ground crew follow. Guidelines dictate how airplanes should approach the gates, when they can take off, and how they should communicate with the control tower. Without these shared rules, an airport would be chaotic. Similarly, in a network, protocols ensure that data packets don't get lost or arrive in the wrong order. Services are like the various operations that keep the airport running smoothly, such as baggage handling, ticketing, and fueling. In the network, services are specialized software applications that use specific ports and protocols to perform tasks like sending emails, loading web pages, or transferring files. Moving data around a network. Imagine employees at a business who get numerous text messages and emails, browse web pages, and make voice over IP, VoIP, calls, which are voice calls that use internet technology. How does the employee email program get only emails, and the text messaging program get only text messages? It would be very odd for emails to show up in the text messaging program. Ports, protocols, and services ensure data makes it to the right place. Introduction. Explore each step to learn about how ports, protocols, and services ensure data travels over a network properly, using an employee email as an example. Step 1. Network interface cards, NICs, make the data ready to send. When an employee sends an email through an email application, their device creates data that needs to get to another device. The application and operating system they are using first sends the data to the network interface card, NIC, which splits it into small chunks called packets. Each packet gets a label with important details such as where it's coming from and where it's going. Step 2. Ports choose the right gate. The data packets are then sent through a specific gate on the employee's device, known as a port. Each type of activity has a different gate it prefers to use. For example, when the employee sends the email, their computer usually uses port 25. Step 3. Protocols set the rules. Before the data packets leave the device, they're given a set of rules to follow, the network's protocol. These rules help determine factors such as the speed at which the data should travel. While the packets might take different routes and arrive out of sequence, the protocols ensure they will be reassembled in the correct order upon reaching their destination. Step 4. Routers send the data out. The data packets begin their journey after getting to the right gate and setting the rules. They travel through different types of networks, from the LAN network in the employee's office to bigger WAN networks that connect cities or countries. Along the way, devices called routers help make sure the data gets to the right place. Step 5. NICs unpack the data. Once the data packets arrive at the device they were sent to, they are unpacked by the NIC on the receiving computer. This means the device's NIC opens the packets to get to the data inside to reassemble them. Step 6. Services make the data useful. Next, the data is given to a specialized helper program on the computer, known as a service. If the data is an email, the email service will take care of it. Step 7. Programs display the data. Finally, the receiver of the employee's email sees the end result on their screen, which is an email message that pops up in their inbox. Ports act like special gates for data, protocols set the rules for how that data moves, and services are the helper programs that manage the data. These three elements work together to ensure data moves safely and quickly from one computer to another. Let's continue to explore network protocols in more detail. Common network protocols and their uses. A woman typing on her laptop. Let's begin by reviewing the following scenario in which Tessa is sending a file to her colleague Raj. You'll learn how multiple types of protocols work together, along with networking hardware, to facilitate data transmission between computers, whether they are in the same office or across the globe. In a corporate office, Tessa sits at her laptop computer, finishing a critical financial report that needs to reach her colleague, Raj, on the other side of the world. She saves the report and prepares to send it. This seemingly simple action initiates a fascinating journey through various protocols defining how networks communicate over local area networks, LANs, and wide area networks, WANs. When Tessa selects Send, the computer sends the file first over the office's LAN. The LAN is governed by protocols like Ethernet, which guide how data packets should be formatted and transferred within the local network. Ethernet allows Tessa's computer to communicate with other devices in the office, such as printers and servers, and the router serves as the gateway to the broader internet. After receiving the data, the router prepares it for its long-distance journey. Here, WAN protocols, such as multi-protocol label switching, MPLS, come into play. There are also Internet protocols like the Transmission Control Protocol, TCP, and the Internet Protocol, IP, that break the financial report into smaller data packets, label them for delivery, and ensure each packet is sent to the correct location and is reassembled correctly once it arrives. These packets then traverse through a series of routers, switches, and sometimes even satellites to reach their global destination. During this stage, WAN-specific protocols are critical in ensuring the data can flow over a complex array of networks and still arrive intact. Finally, Raj's computer receives these data packets. The LAN protocols reformat the packets back into the original file, and he opens Tessa's financial report, which has gone through a complex web of LAN and WAN protocols that brought it to him. You can conclude from this scenario how data packets undertake a complex journey, guided by specific rules determined by network protocols. These protocols ensure that the data is properly formatted, transmitted, and reassembled. The two most common networks are LANs and WANs. Let's explore their characteristics and how protocols are used in these networks in more depth. LAN protocols. Notice in the diagram how data flows over a LAN using various protocols. For example, email data from a sender starts from a laptop and flows through an application layer, using HTTP, a transport layer, using TCP, a network layer, using IP, and a data link layer. It then moves through an Ethernet cable and follows the same path in reverse to the receiving device on the LAN. A diagram illustrating various protocols for LAN networking. Data flows from a laptop through an application layer, HTTP, a transport layer, TCP, a network layer, IP, and a data link layer. It then moves through an Ethernet cable and follows the same path in reverse to the target device on the LAN. Recall that protocols define the procedures and formats that devices like computers and routers must follow to make sense of the incoming data and know what actions to take. LANs use specific protocols that devices use to send and receive data. Some data travels only within a LAN, moving from one device on the LAN to another. Other data travels outside the LAN to a WAN like the Internet. Still, other data travels from the LAN through a WAN to another LAN. Regardless of the journey, all LAN devices use specific protocols with unique characteristics to ensure the data journey is successful. Let's explore the characteristics specific to LAN protocols that make them ideal for working in a local network. High speed. LAN protocols are designed for quick data transfer. Speeds range from 100 megabits per second up to 40 gigabits per second. This means computers in the same local network can quickly share files and information. Short geographic scope. LAN protocols work best over small distances. They are ideal for networks that connect devices within a single building or a cluster of nearby buildings. Broadcast capabilities. LAN protocols enable one device to send a message that reaches all other devices on the network at once. This ability is useful for quick communications about updates or important announcements. Flexibility. LAN protocols offer many options for customization. Engineers can configure the network to meet an organization's specific needs, such as enabling certain security features or setting up specialized subnetworks. Error handling. LAN protocols provide basic error detection but rely on other protocols for error correction. However, because of their confined geography, LAN networks are usually very dependable, so their protocols don't have to focus much on fixing errors in data transmission. WAN protocols. In many cases, LAN networks are connected by WAN networks. When someone sends you an email from their home LAN to your home LAN, the data passes over the Internet, which is a WAN. Notice in the following diagram how the Internet combines two separate LANs into a connected WAN network. It shows multiple devices connected by switches and routers. Data passes over the Internet to another router with devices connected to another LAN network. A diagram illustrating two LANs connected over a WAN network. Multiple devices including televisions, laptops, and tablets, are connected by switches and routers on one side. Data passes over the Internet to another router with devices connected to another LAN network on the other side. Large networks that handle data that travels long distances through many different types of network hardware need protocols that can handle the various challenges the data can face. Suppose you're taking a short flight from one city to another in your country and don't need to switch planes. Baggage attendants put your bags on the plane in your departure city and take them off in your destination city. If you're taking an international flight with layovers and plane changes, your bags will go through different procedures to reach your destination. The airlines need different rules to process your luggage for the international flight than they would for the short, domestic flight. Similarly, WAN protocols are specifically designed to handle transferring data over a wide area. Let's explore the characteristics specific to WAN protocols that make them ideal for sending data over long distances. Long-distance routing. WAN protocols handle sending data across long distances, sometimes across countries or continents. They decide the best route for data and can change the route as needed. Data rate adaptability. WAN protocols are designed to work well in different conditions, allowing data to be sent at varying speeds. They can adjust based on how busy or slow the network is at any given time. Complex routing algorithms. WAN protocols use advanced methods to determine the most efficient way to send data from one point to another. They do this by constantly evaluating different paths and selecting the best one at that moment. Packet labeling and prioritization. WAN protocols can label data to give some items priority over others. For example, a live video stream might be given priority over email or text communication to ensure it plays without interruption. Error correction. WAN protocols have special features to detect and correct errors. Because data travels long distances, sometimes errors occur. These error correction mechanisms ensure that data arrives intact. Encryption and security. WAN protocols often have built-in security features to protect data as it travels across networks without the sender's control. This includes encrypting the data to make it harder for unauthorized users to read it. Multi-layer functionality. WAN protocols perform tasks at different stages of data transmission, which happen at different layers of network communication. WAN protocols are involved in all the stages, from sending data to receiving data at its destination. Virtual connections. WAN protocols can set up dedicated routes for sending data. These established pathways help maintain a consistent and reliable flow of information. They are virtual because they focus on the logic of how data flows rather than the physical pathways. LAN and WAN protocols form the foundation of network communication within local and wide area networks. In addition to LAN and WAN protocols, there are a variety of Internet protocols, such as HTTP, TCP/IP, and File Transfer Protocol, FTP, that work across both types of networks to transfer data. Let's explore these Internet protocols. Internet protocols that work across networks. An illustration of network nodes with connecting lines spanning a sphere representing the world. Image source, image by Gerd Altman, opens in a new tab, from Pixabay, opens in a new tab. Along with LAN and WAN protocols, Internet protocols work in both LANs and WANs and are consistent in both environments. These Internet protocols are broad enough to handle the complexity of data that must travel over a wide area or a local area. Specifically, Internet protocols include TCP/IP, HTTP, Hypertext Transfer Protocol Secure, HTTPS, FTP. These protocols can operate over both types of networks. Let's explore each of these. TCP/IP. TCP/IP is one of the most widely used and powerful pairs of networking protocols that network architects use today. In the following diagram, notice that the puzzle pieces represent data being broken up into packets. The diagram shows how, using TCP/IP, the network can ensure the data on the sending side is reassembled in exactly the same way on the receiving side, even after it's sent over the Internet. A diagram illustrating data as a puzzle with individual pieces on a sending laptop. The puzzle is broken up into individual, numbered pieces that are each a different color. They are sent over the Internet represented by a globe. An arrow and individual puzzle pieces represent the data packets being transmitted. The puzzle is then reassembled on the receiving side represented by the same puzzle on the receiving laptop. TCP/IP defines the rules for sending and receiving information over the Internet. It makes sure that your messages or files arrive at their destination safely and in the right order. It works behind the scenes to manage the basic transfer of data between computers and other devices connected to the Internet. One of TCP/IP's essential features is the three-way handshake. Imagine it as a polite conversation between two computers before they exchange data. First, one computer says hello, and the other replies, "Hello, I'm ready." Then, the first computer confirms, "Great, let's talk." This handshake ensures a secure connection before your data starts its journey, making the Internet a reliable place for information exchange. TCP/IP operates in layers to handle various aspects of network communication. The Transmission Control Protocol, TCP, breaks down large pieces of data into smaller packets and tags them with sequence numbers for reassembly. These packets are then sent over the network and reassembled at the destination. TCP ensures that all packets arrive and the receiving device reassembles them in the correct order. It also retransmits any packets that go missing along the way. 1. Before each packet is sent, the Internet Protocol, IP, is responsible for labeling each packet with an IP address that identifies both the sender and receiver. 2. Routers then examine the destination IP address to route these packets to their final destination. 3. The protocols guide each packet through the complex network of routers and switches to ensure it reaches the right place. Together, TCP and IP create a reliable system for transmitting data across potentially unreliable networks. TCP/IP provides the rules for how data flows over a network. Networks need other protocols to know how to handle specific types of data, and that's where HTTP, HTTPS, and FTP come in. TCP/IP is like the airline that ensures a passenger's luggage makes it to their destination safely and in the right order. HTTP, HTTPS, and FTP are like the specific rules and regulations that guide the airline on how they should specifically treat luggage during transport. HTTP. The original idea of the web was that it should be a collaborative space where you can communicate through sharing information. Tim Berners-Lee opens in a new tab, inventor of the HTTP protocol. HTTP, or Hypertext Transfer Protocol, is the primary protocol for transferring data over the web. It is a set of rules that govern how information should move between your computer and the web server where a website is hosted. Imagine you're at a library. You approach the librarian, your browser, and request a specific book, a website. The librarian then fetches the book from the shelves, the web server, and hands it to you. Similarly, in the digital world, when you want to visit a website, you open your browser and type in a URL. Your browser acts as the librarian, retrieving the website's data from the web server and presenting it to you. HTTP is the established set of rules and interactions that enable the browser and the web server to provide you with the website you requested. It ensures the browser knows where to find the website and how to bring it to you. Here's what happens when you enter a web address in your browser or click a link. 1. Your browser sends an HTTP request to the web server to request the web page you want to see. 2. The server reviews the request and looks for the relevant web page. 3. If the page exists, the server sends it back to your browser with an HTTP response. 4. Your browser translates that response into the web page that you see. The following diagram illustrates how data flows over a network using HTTP. Notice how the client device, such as a cell phone browser, makes a request to a server. The server then sends a response back to the client device. A diagram illustrating the client device on the left and a server device on the right. The client makes a request to a server, illustrated by an arrow pointing to the server. The server then sends a response back to the client device, illustrated by an arrow pointing to the client device. Whether connecting to an internal website within your local company network, LAN, or accessing a website hosted on a server halfway across the globe, WAN, HTTP provides a universal set of rules that make this communication possible and efficient. HTTPS. One of the most important developments in web technology and data security has been the implementation of Hypertext Transfer Protocol Secure, HTTPS. HTTPS is a secure version of HTTP and is used for secure communication over a computer network, usually the Internet. A child writing a note. As a child, you might have developed a secret code with friends. You might have replaced letters with numbers or replaced letters with symbols. In other words, you would send encrypted messages to each other. Encrypted messages are called ciphers. To write or read a cipher, you must have something that helps you translate between the cipher and natural language. That something is a key. Encryption is a method used to scramble important data and information so unauthorized individuals or devices are unable to understand the information without a decryption key. Data transferred using the HTTPS protocol is encrypted, and a special key is used to decrypt it. With the advent of large networks, using HTTPS to transfer data over networks keeps data more secure. When you enter a web address using HTTPS protocol in your browser or click a link, here's what happens. 1. Your browser initiates a secure connection with the web server by exchanging encryption methods and keys. 2. The browser and web server agree on an encryption method and create a unique session key. 3. With encryption in place, data is divided into small packets using TCP and encrypted using the agreed-upon method and key. 4. The server proves its authenticity using a digital certificate issued by a trusted authority. 5. The browser uses the encryption key agreed upon, transforms the data back into its original format, and renders the page. The following diagram illustrates how data flows over a network using HTTPS. Notice how the client device makes a request to a server like the HTTP protocol. The server then sends a response back to the client device. However, using HTTPS, the data request is encrypted when it's sent and received, as illustrated by the locks. A diagram illustrating a client device on the left and a server device on the right. The client makes a request to a server, illustrated by an arrow pointing to the server. The server then sends a response back to the client device, illustrated by an arrow pointing to the client device. At the sending side of both, the client and server has a red lock, illustrating the data being encrypted. At the receiving side of both, the client and server has a green lock, illustrating the data being decrypted. HTTP was developed primarily to transfer smaller text-based files, making it very efficient at transferring such data. However, when it comes to larger or more complex file types, like documents and images, HTTP's efficiency diminishes. This limitation led to the development of File Transfer Protocol, FTP. FTP. File Transfer Protocol, FTP, is another way of transmitting data over the Internet. Unlike HTTP, which primarily serves the purpose of displaying web pages in your browser, FTP specializes in the efficient transfer of various file types, including documents, images, or software, among computers. FTP transfers files between a computer and a server, and it can operate over any TCP/IP-based network, whether it's a LAN or WAN. Like HTTP, the File Transfer Protocol has two variants. File Transfer Protocol Secure, FTPS, encrypts file transfers and FTP does not. Most cloud providers only support FTPS. FTP is used less and less in today's computing environment. Select each section to learn more about the features of FTP. Two-channel system. FTP uses two separate channels for communication, one for sending commands and another for transferring data. Authentication. FTP protocols often require supplying a username and password to access files, offering a layer of security. File management. The FTP protocol allows users to create, delete, and rename folders or files on the server, offering more control over file organization. Binary and text modes. FTP supports different modes for transferring data, enabling more efficient transfers depending on the file type. Binary data is typically data like audio and video files that only computers can read. Text files have human-readable text data. Passive and active modes. FTP can operate in either passive or active mode, which affects how the connection between the client and server is established. In active FTP mode, the server initiates the data connection with the client, which can cause issues with firewalls. In passive FTP mode, the client initiates the connection to the server, making it more firewall-friendly. Batch transfers. The FTP protocol is designed to handle multiple file transfers simultaneously, making it efficient for transferring large volumes of data. Directory listing. Users can view a list of files and folders on the server using the FTP protocol, much like exploring folders on their own computer. Resume capability. If a file transfer is interrupted, the FTP protocol can resume from where it left off, saving time and bandwidth. The features of the FTP protocol make it ideal for sending large files that cannot easily be shared using email. For example, say you have a large graphic design file that is too big to send using email. When you share that file using an FTP client, here's what happens. You log into the FTP client using a username and password to establish a secure connection with the FTP server. If you use FTPS, your communication with the server will be encrypted. If you use FTP, your communication with the server will not be encrypted. 2. FTP uses the command channel to initiate the file transfer, send instructions, and manage the file transfer session. 3. FTP opens a separate data channel. 4. The large graphic design file is divided into smaller segments known as packets using TCP. These packets are sent over the data channel and reassembled on the server side. 5. Once the file transfer is complete, The FTP server sends a confirmation message indicating that the file has been successfully uploaded to the server. 6. The uploaded graphic design file is stored on the FTP server and is now available for authorized users to access and download. 7. Authorized users can connect to the FTP server using their own FTP client, authenticate, and download the file using a similar process in reverse. The following diagram shows how data flows between an FTP client and an FTP server. Notice that the data flows both ways and shows how FTP uses two channels, one for data and one for commands. A diagram illustrating that data flows both ways between an FTP client, illustrated by a laptop, and an FTP server, illustrated by a server stack. There are two bidirectional arrows connecting the client and server to illustrate how FTP uses two channels. One arrow is labeled control channel and one arrow is labeled data channel. Activity: use HTTPS to access a website securely. Employability skills. Creative thinking. In this activity, you'll apply what you just learned about how Internet protocols work by placing the steps that happen in sequential order as you access a secure website on a network. Imagine you're the IT support technician for your company. You need to check the compatibility of a new software update with your organization's network infrastructure. Before you start your compatibility tests, your manager asks you to review how encrypted data flows over the network using the HTTPS protocol. Summary and looking ahead. In this lesson, you learn the role of ports, protocols, and services in network communication. You learned how these components work together to ensure data travels safely and efficiently over networks. You also learned the characteristics of LAN and WAN protocols and common Internet protocols including TCP/IP, HTTP, HTTPS, and FTP. These protocols enable data transfer over both local and wide area networks, ensuring security and efficient communication. The next lesson covers LAN technologies and protocols in more detail. About this lesson, LAN protocols. Imagine the early days of computing when data was transferred from computers manually by physically carrying the data from one computer to another. Consider the game-changing innovation brought by local area networks, LANs. LANs have empowered efficient communication, resource sharing, and data access within confined areas. In this lesson, you'll learn how LAN technologies enable efficient communication within a confined area. You'll explore key LAN protocols like Ethernet, Token Ring, and FDDI, along with IP addressing, DHCP, APIPA, and IP reservations. You'll also explore how to optimize network performance by configuring and managing IP addressing, and you'll learn the steps to setting up a DHCP server. An introduction to LAN technologies. In the early days of computing, the ability to share information was limited by the need to manually transfer data between devices. The development of LANs was a game-changing advancement that allowed multiple computers within a confined area to communicate, share resources, and access data seamlessly. These networks serve as the backbone for a variety of tasks, from file sharing in a small office to high-speed data transfer in large campuses. The technologies that power LANs have evolved over time, adapting to meet the ever-growing demands for speed, reliability, and security. Engineers have developed various structures to move data over a network. A structure for data flow is called a network topology. Think of a network topology as a highway design. Like traffic flowing over roadways, the design of the topology determines how data flows over a network. Since LAN networks make up many office environments, IT support technicians might encounter network connectivity problems or data transmission errors. They might also be involved in network installation or maintenance. Understanding LAN networking technologies can help technicians diagnose and resolve networking issues, and ensure proper network configuration, optimization, and installation. In the world of LANs, Ethernet, Token Ring, and Fiber Distributed Data Interface, FDDI, are three types of technologies or roads that help data get to where it needs to go. Let's explore each of them. Exploring LAN technologies. LAN technologies are fundamental to modern networking, enabling efficient communication and data sharing within a limited geographical area. Let's examine the following LAN technologies. Ethernet. Token ring. FDDI. Ethernet. An Ethernet network is a common way to connect computers and other devices within a confined geographic area, such as an office or home. It usually involves physical cables, often made of copper or fiber optic material, that are used to link devices. Think of Ethernet as a set of rules or a language that these devices use to communicate with each other. Ethernet specifies the rules for transmitting data over various cables. Ethernet is known for being straightforward and dependable, making it the preferred choice for many local area networks. It provides a balance of speed, reliability, and cost-effectiveness that suits a wide range of needs. What do IT support technicians need to keep in mind? Because of its widespread use, Ethernet-related issues, such as connectivity problems, network configuration, and cable faults, are frequent support requests. IT technicians need to understand how Ethernet technology works to properly diagnose and resolve these types of issues. Select each section to learn more about the features of Ethernet networks. What it does. Ethernet is a popular technology for creating a local network in offices or homes. Through physical cables, it connects various devices such as computers, printers, and routers, allowing them to communicate with each other. How it works. Imagine Ethernet as a postal system for digital data. It doesn't just randomly toss letters and packages, data, out of a truck. Instead, data is transmitted in Ethernet frames, which consist of a header, payload, and trailer. The header includes source and destination MAC addresses, while the trailer contains error-checking information. The payload contains the data being transmitted. Ethernet sorts these frames into specific orders and routes, delivers them through the network cables, and reassembles them at the other end, ensuring each data packet reaches its correct destination efficiently. Ethernet uses a method of data transmission where devices can send data whenever they have data to send. There isn't a strict order or control mechanism dictating when devices can transmit. Devices on an Ethernet network can attempt to send data simultaneously, which can lead to collisions and the need for collision detection and resolution mechanisms. Typically, if there are no data packets being received, the device considers the network to be quiet and might attempt to send its own data. Topology. Ethernet mainly uses a star topology. There is a central node, typically a router or switch, connected to all other nodes, which can be other routers, switches, computing devices, or peripherals. A node refers to any network component or device that is connected to the Ethernet network. Each device on the network has its own separate cable that connects to the central node. This increases reliability because if one cable experiences a failure, it does not affect the functionality of the other connected devices. Speed. Ethernet networks offer various speeds, ranging from older standards like 10 or 100 Mbps to today's speeds of up to 40 Gbps. To put it in perspective, on a 100 Mbps connection, you can download a 700 megabytes movie in about 56 seconds. However, with a 40 Gbps connection, the same download takes just 1 second. For larger files, like a 5 GB video, the difference is even more striking: 7 minutes on a 100 Mbps connection versus 1 second on a 40 Gbps connection. Imagine a massive 100 GB file, such as an AAA game or a complex AI model. It would take over 2 hours to download on a 100 Mbps connection but just 20 to 25 seconds on a 40 Gbps connection. Ethernet speeds, influenced by cable types and device capabilities, have a profound impact on data transfer times for large files and data-intensive tasks. How it's unique. Ethernet is unique in its simplicity and reliability compared to other LAN technologies. Ethernet is the preferred choice for many local networks in homes and businesses because of its straightforward setup and reliable performance. The following diagram illustrates an Ethernet network. Notice the switch is at the logical and physical center of the network so that all data flows through the switch before it's sent to another device on the network. Data flow is represented by lines connecting the devices to the switch. While Ethernet is a widely adopted technology known for its simplicity and reliability in local networks, there are other LAN technologies that IT support technicians must be familiar with. Some organizations have older networking technologies or use a mix of networking technologies to meet specific needs, and being familiar with these technologies can help technicians be prepared to support and troubleshoot a variety of issues. Next, you'll explore an older LAN technology called token ring, which is still used in some networks today. Token ring. A token ring network is a type of LAN that connects devices, using cables, in a closed loop or circle. Each device is connected to two neighboring devices. Similar to Ethernet, token ring is a set of rules that these devices use to communicate with each other. Token ring specifies how devices pass a token to gain permission to transmit data, how data packets are formatted, and how devices address and access the network. While not as commonly used today as Ethernet, token ring networks offer a high level of control and can be found in environments that require specific network configurations. What do IT support technicians need to keep in mind? Even though token ring is less commonly used today, IT support technicians need to understand how networks that operate using token ring technology work. They might need to support specialized or legacy networks or equipment that rely on token ring technology. Legacy refers to older, outdated technologies that were once widely used but have been largely replaced by newer alternatives. Plus, in some cases, organizations might have hybrid network environments that include both token ring and more modern technologies, such as Ethernet. IT support technicians might need to ensure that these technologies can coexist and communicate effectively. Select each section to learn more about the features of token ring networks. What it does. A token ring network connects devices in a network into a circular or loop-like structure, allowing them to communicate with each other. It is less commonly used today but still operational and found in some legacy systems or environments where updating the network isn't feasible. How it works. Token ring uses a ring topology to connect network devices in a closed loop. Unlike Ethernet, which doesn't have a strict control mechanism for when devices can send data, token ring employs a more organized approach. Devices must wait for a special, small piece of data, called a token, that circulates around the network. The token grants permission to each device to send its information, and only the device that holds the token can transmit data at any given time. Once a device has used the token, it is passed to the next device in the loop. This organized system minimizes data collisions, ensuring smoother data transmission. Topology. In a token ring network, the topology is structured as a closed loop. This means that each network device is connected to exactly two other devices, one device before it and one device after it in the sequence. Data circulates around this loop in one predetermined direction. The loop is closed because the data can continue to circulate indefinitely until it is received by the correct device. This closed loop structure is fundamental to how token ring manages data transmission and minimizes data collisions or data becoming garbled by running into other data. Speed. Token ring typically offers slower speeds compared to modern Ethernet networks. While token ring can operate at speeds such as 4 Mbps or 16 Mbps, it usually can't match the high speeds of today's Ethernet networks, which can go up to 40 Gbps. How it's unique. Token ring's unique strength lies in its disciplined approach to data transmission. Because only one device can send data at a time using the token, collisions or data crashes are avoided. However, this also means the system can be less efficient, as devices must wait their turn to communicate. The following diagrams shows how a token ring network moves data around the network. Notice the diagram shows a single token that gets passed from device to device in the network in a single direction of flow. Only one device can have the token at a time. Fiber Distributed Data Interface, FDDI. A fiber distributed data interface, FDDI, network was designed for larger local area networks that needed to cover significant distances, such as large campuses or multi-story buildings. FDDI uses fiber optic cables, allowing high-speed data transmission over longer distances than traditional copper cables. The network operates in a ring formation similar to a token ring, but has an additional layer of reliability, a secondary, or dual, ring. If the primary ring encounters a problem, the dual ring takes over to keep the network running smoothly. This feature, along with the high-speed capabilities of fiber optic cables, makes FDDI particularly reliable and well-suited for environments that require both speed and dependability. What do IT support technicians need to keep in mind? Similar to token ring, FDDI is less commonly used today. The technology was developed in the 1980s and newer technology offer better speeds and efficiency. However, it is helpful for IT support technicians to understand how FDDI networks operate. Some organizations might still have FDDI networks in place, and technicians might need to provide support and troubleshoot issues with these networks. Select each section to learn more about the features of FDDI networks. What it does. FDDI was designed for networking over larger areas, such as sprawling campuses or multi-story office buildings. It relies on fiber optic cables, which are capable of transmitting data at high speeds over long distances. How it works. FDDI employs a ring-based system similar to token ring, where devices are connected in a closed-loop system. But each device has two fiber optic connections that add a layer of security, a dual ring. Imagine a highway with a regular lane and an emergency lane. If there's a breakdown in the regular lane, the main ring, traffic is diverted to the emergency lane, the dual ring. This ensures the network stays up and running, even when there are issues. Similar to token ring, devices on the network must wait for a token to transmit data. Topology. In FDDI, the topology consists of two concentric rings, a primary ring and a secondary ring. These rings are made up of a series of connected devices. Data typically flows in opposite directions on each ring, providing an automatic backup route for data transmission if one of the rings fails. This creates a highly resilient network structure. Speed. FDDI networks offer speeds of up to 100 Mbps. Fiber optic cables allow for higher speed than traditional token ring networks and support larger data packets, making the network more suited for heavy data transmission tasks. How it's unique. What sets FDDI apart is its exceptional reliability and the ability to cover large distances, thanks to its dual ring topology and fiber optic cables. This makes it a strong choice for environments where both high speed and high reliability are essential. In the following diagram, notice the FDDI network includes devices outside two circles connected by lines that go from one device to the next. It also shows the flow direction of one circle moving in a clockwise direction and the other moving in a counterclockwise direction to support greater speed and reliability over a simple token ring network. You've learned about how LAN technologies, such as Ethernet, token ring, and FDDI, enable devices on local area networks to communicate. Now, let's explore another fundamental component of networking protocols, IP addresses. IP addresses and allocation. Busy street in New York City with tall buildings, pedestrians, taxis, cars, and street lights. Imagine walking around a busy city where every building looks the same, but each has a specific address. You'd need to know those addresses to find your way around, right? In the digital landscape, IP addresses serve a similar purpose. An Internet Protocol, IP, address is a unique string of numbers and dots that identifies the network, or subnet, as well as the individual computer or device connected to the network. Think of an IP address as the postal address for your home in the digital world. An IP address ensures that data goes to the right location when you send or receive data. IP addresses play a significant role in LAN protocols by providing a structured addressing scheme that allows devices within a LAN to communicate with each other and with devices on other networks. In a LAN, each device, such as a computer, printer, or router, is assigned a unique IP address. This IP address distinguishes each device on the network, ensuring that data is directed to the correct destination. Subnets. Suppose that a friend's home network has 10 devices connected to it. Each device has a unique IP address on that network. Your friend looks up the IP address for one of their devices. This is something that they can do from a terminal window or the router's software. They discover that the device's IP address is 192.168.1.10. You then look at all the devices on your home network and discover that you also have a device with the IP address of 192.168.1.10. How can this be? How can two devices on separate networks have the same IP address and still get the data they need from the internet? It's because routers use subnets. When a router on one network assigns a device an IP address, those IP addresses are not seen outside that network. Your router faces in toward your network providing IP addresses for each of your devices. Your network is called a subnet because it's a network that is inside another network, the internet. Subnets are like cities. Just as homes in two cities can have the same address, like 123 Maple Avenue devices on different subnets can have the same IP address. A subnet is an address for a network within a network. The subnet helps routers to sort and send information to its destination. The makeup of an IP address. LAN protocols, such as Ethernet, use media access control, MAC, addresses to manage local data transmission within the LAN itself. IP addresses come into play when data needs to be routed outside of the LAN. Routers within the LAN examine the destination IP address to determine the appropriate route for data leaving the LAN. An IP address typically comprises 4 sets of numbers separated by dots. For example, it might look something like 192.168.1.1. Each set is called an octet and can range from 0 to 255. This structure is specific to what's known as Internet Protocol version 4, IPv4, which is the most commonly used form of IP addressing today. There's also IPv6, a newer version designed to address the limitations of IPv4, mainly its limited number of unique addresses. While there is a large but limited number of unique IPv4 addresses, there are essentially an unlimited number of unique IPv6 addresses available. An IPv6 address is much longer and can look like this. 1200:0000 of 00:1234:0000:2552:7777:1313. These characters represent different parts of the network and devices to make up the unique address. Network prefix, the first few groups, usually the first 3 or more, represent the network prefix. This part of the address identifies the network or subnet to which the device belongs. It's similar to the network portion of an IPv4 address. Interface identifier, the remaining groups, typically the last 5 or fewer, represent the interface identifier. This part identifies a specific device or interface within the network. It's often derived from the device's MAC, media access control, address. The significance of IP addresses in IT support. A woman wearing headphones having a video call on her desktop monitor with co-workers and writing down notes. IT support professionals need to understand IP addresses when managing and troubleshooting computer networks and devices. Understanding IP addresses is useful when identifying devices, troubleshooting networks, and securing networks. Select each tab to learn more about how IT support technicians work with IP addresses. Identify devices. IT support technicians use IP addresses to identify and locate specific devices on a network. This is important for remote troubleshooting, device management, and security monitoring. Troubleshoot networks. IT support professionals often need to diagnose and resolve issues when users encounter network connectivity issues. Understanding IP addresses is essential for identifying misconfigured addresses, subnetting issues, or IP conflicts that can disrupt network communication. Secure networks. IT support professionals must be able to recognize suspicious IP addresses or traffic patterns that might indicate security threats, such as malware infections, intrusions, or unauthorized access attempts. IP addresses are a critical component of computer networking, and IT support professionals require a deep understanding of IP addressing to fulfill their responsibilities effectively. Whether identifying devices, troubleshooting networks, or securing networks, a strong understanding of IP addresses is essential for providing reliable IT support. But how do devices obtain an IP address? IP addressing. Every device that's connected to a network receives an IP address, which is a unique set of numbers that allows it to send and receive information. Understanding IP addresses and how they're assigned is critical because they are the digital coordinates that make sure data gets to the right destination. There are different methods for how devices can get IP addresses, and the methods and addresses themselves have special features. Each address type plays a unique role in ensuring devices can be found on a network. Select each section to learn more about different types of IP addressing on LAN networks. Dynamic Host Configuration Protocol, DHCP. Imagine visiting a city for the first time, and a helpful guide immediately gives you a temporary address. That's what DHCP does for devices on a network. A DHCP server typically handles the task of address assignment on a network. This device or software dynamically distributes IP addresses to computers and other devices as they join the network. It's a convenient, hands-off approach that handles the technical details for you. Automatic Private IP Addressing, APIPA. What happens if DHCP isn't available? That's where APIPA comes in. Automatic private IP addressing is like giving yourself a makeshift address when no one's around to assign one. If a device can't find a DHCP server, it assigns itself a temporary IP address. This temporary solution allows basic network functions but lacks the full capabilities of a DHCP assigned address. For example, a device with an APIPA address might be unable to connect to the Internet. IP reservations. IP reservations are like exclusive addresses in this imaginary city. A network administrator sets up these specially reserved, permanent addresses for specific devices. For instance, a printer in an office might have a reserved IP address so that everyone can easily find it every time. It provides consistency and helps streamline network management. IP addressing is the map of digital communication, enabling devices on a network to find each other and exchange information. Whether it's the automated convenience of DHCP, the fallback mechanism of APIPA, or the consistent reliability of IP reservations, each plays a unique role in making the digital world function seamlessly. What do you think? Critical thinking. You've learned about the importance of IP addresses in networking and providing IT support for network issues. In your own words, how would you explain what an IP address is to a friend or family member? Evaluate your thinking. Does your answer account for the following? IP addresses are similar to a postal address. Just as a postal address identifies a unique house or building in a city, an IP address identifies a unique address on a network. Maintaining an optimized network by configuring IP addressing. Maintaining a well-functioning network requires careful planning, especially regarding IP addressing. A poorly managed IP address system can lead to network errors and inefficiencies. Network administrators or IT support professionals must configure IP addressing in most network environments. Let's explore this further using a scenario. A woman working on a computer in a server room. Imagine you've just landed an IT support technician role at a mid-sized company. On your first day, you discover network performance isn't up to par. Employees are complaining that the internet is slow, printers are periodically disconnecting, and, to top it all off, The server has crashed twice this week. You investigate and find that the network's IP addressing system hasn't been configured. You're tasked with the initial configuration and management of IP addressing to improve overall performance. Step 1. Conduct a network audit. First, you must make a list of all the devices connected to the network: computers, printers, smartphones, and other smart devices. Document their current IP addresses, if available. Knowing what's on the network is crucial for effective management. Step 2. Choose between static and dynamic IP addressing. Decide which devices should have a static, or permanent, IP address and which can have a dynamic, or temporary, one. Typically, servers and printers get static IPs for easier access, while personal devices like laptops can have dynamic IPs. Step 3. Set up a DHCP server. Install or designate a DHCP server. In small networks, this is often your router. This server will automatically assign dynamic IP addresses to devices when they join the network, freeing you from having to manage this manually. Step 4. Configure IP reservations. Set up reservations on your DHCP server for devices requiring static IP addresses. This ensures these devices always receive the same dedicated IP address, making them easier to find and manage. Step 5. Create an IP addressing scheme. Develop a logical system for your IP addresses. For instance, you might reserve the first 10 addresses for servers, the next 20 for printers, and so on. Having an organized scheme helps you easily identify devices and troubleshoot issues. Step 6. Implement subnetting, optional. Subnetting, which groups devices logically, makes it easier to manage, secure, and control traffic within the LAN. For larger networks, consider dividing your network into smaller, more manageable pieces known as subnets. This can make the network more efficient and secure. On large LANs, it also can increase the number of devices an enterprise can add to their network. Step 7. Test the configuration. Before fully implementing the changes, test your configuration to ensure everything works as expected. Connect various types of devices to see if they get the correct type of IP address, whether static or dynamic, and that data flows smoothly. Step 8. Monitor network performance. Regularly check your network's performance. Look for signs of slowdown, unexpected disconnect ions, or other issues indicating an IP addressing problem. Step 9. Monitor IP addressing. Technology changes quickly, and your network will too. Consistently review your IP addressing scheme to ensure it fits your current needs. Update it as necessary, especially when introducing new types of devices. Proper IP address management might not be something users are aware of, but they'll definitely notice when it's done poorly. While each step is important, setting up a DHCP server properly is central to reliable IP addressing and deserves special attention. Setting up the DHCP server supports an optimized and properly functioning network. Setting up a DHCP server. Imagine it's your second week as an IT support technician, and you're looking to streamline network connectivity. Employees are currently waiting too long to get online due to manual IP address assignment, which is also prone to errors like address conflicts. Your next task is to set up a DHCP server. This server will automate the IP address assignment process, ensuring each device has a unique identifier for smooth communication. By configuring the DHCP server, you'll make the network more efficient, reduce errors, and expedite the connection process for all employees. Step 1. Determine the device to act as a DHCP server. First, you'll need to decide what device will act as your DHCP server. In many small networks, the router can act as a DHCP server. For larger networks, you might need a dedicated computer to perform this function. Step 2. Access the configuration interface. You'll need to log into the device that will become your DHCP server. This usually involves opening a web browser, typing in the IP address of the device, and entering a username and password. The exact steps might vary depending on the device you're using. Step 3. Locate the DHCP settings. Once you're logged into the configuration interface, find the DHCP settings. This is usually under a section labeled Network Settings, LAN Setup, or something similar. Step 4. Enable the DHCP server function. Look for an option that allows you to enable or disable the DHCP server function. Make sure it's enabled. Some interfaces will also allow you to specify the range of IP addresses the server can assign. This should align with your IP addressing scheme decided earlier. Step 5. Configure IP address range and lease time. Set the range of IP addresses that can be assigned dynamically. You'll also set a lease time, which is how long each device can keep its IP address before it must ask for a new one. The default is often 24 hours, which is generally fine for most networks. Step 6. Set up reservations, optional. If you have devices that need a permanent IP address, such as printers or servers, you can usually set up reservations within your DHCP settings. This ensures that these devices will always be assigned the same IP address. Step 7. Save and restart. Once all settings are configured, save them and restart your DHCP server or device, if necessary. This will apply all the changes you've made. Step 8. Test the configuration. To ensure everything is working as it should, connect a device to your network. It should automatically receive an IP address from the range you specified. Check that this is happening to confirm that your DHCP server is functioning correctly. You've explored how to configure and manage IP addressing to optimize a network and how to set up a DHCP server. Next, you'll practice setting up and configuring IP addresses by working alongside an expert for a company's office space. Activity: configure and manage IP addressing. Employability skills: analytical thinking, collaboration, and teaming. In this activity, you are an IT support technician that has the opportunity to shadow Alex, a senior IT support technician at a large cybersecurity firm. Today is an exciting day. Your main task for the day is to assist Alex in setting up and configuring IP addressing for the company's new office space. This will involve several crucial steps, and as you work through them, you'll assist Alex by using your knowledge of configuring IP addressing. You'll answer questions as you perform the steps to configure IP addressing. Conducting a network audit. Alex explains that the first step is to conduct a comprehensive audit of the network. You work alongside Alex to list all the devices currently connected to the network: servers, computers, printers, smartphones, and other smart gadgets. This audit will help you and Alex as you move forward so that you can effectively manage IP addresses. Illustration of two people, one holding a magnifying glass, in front of a clipboard that states, Audit. Choosing between static and dynamic IP addressing. After the audit, Alex talks to you about how to approach IP addressing. The office has critical hardware like printers, desktop workstations, and servers. But, the company also has a bring your own device, BYOD, policy in which employees are able to use personal devices like smartphones and laptops. Illustration of two people having a conversation. One chat bubble states static IP address and the other states dynamic IP address. Setting up a DHCP server. Next, Alex walks you to a modest, but powerful server rack. He points out the machine that will act as the DHCP server. It's time to assist in configuring the DHCP settings, ensuring that the server is programmed to automatically assign dynamic IP addresses to devices as they join the network. Configuring IP reservations. Alex then brings up the DHCP management console and explains how to set up IP reservations. He shows you how to ensure that devices requiring static IP addresses will always receive the same dedicated IPs, making them easier to manage in the long run. Creating an IP addressing scheme. Moving back to the main console, Alex emphasizes the need for an organized IP addressing scheme. Together, you set up a logical structure that reserves the first 100 IP addresses for servers, the next 20 for printers, another 30 for desktop workspaces, and the remaining addresses for personal devices like smartphones and laptops. Implementing subnetting. Alex notes that for larger networks, like the company you work for, subnetting can be invaluable. He takes some time to explain the concept and shows you how to logically group devices and configure the subnets to make the network more efficient and secure. He explains that subnetting helps improve security by separating parts of the network and control who has access. This makes it easier to set up firewalls, monitor for suspicious activity, and keep important data more secure. Testing the configuration. Before wrapping up, Alex insists on testing the new configuration. You help by connecting various devices to the network, ensuring that each receives the correct type of IP address, either static or dynamic, and that data is flowing without issues. To test the network, you check one of the printers on the network to see if it has been properly assigned an IP address. To do this, you go into Settings while connected to the network and review the printer properties. On the Web Services tab, you review the following information. Was your test successful? Does the printer have an assigned IP address? Well, you know that the server is set up to provide IP addresses using Internet Protocol version 4, IPv4. You know that IPv4 addresses are made up of sets of numbers called an octet. Each set can include a number that ranges from 0 to 255. Monitor network performance. As you near the end of your shadowing experience, Alex sets you up with some monitoring tools. He explains that these tools will help you watch and track the network's performance over time, ensuring that everything continues to run smoothly. In conclusion, a careful audit and a strategic approach to IP addressing enables devices to easily connect to the network, makes it easier to locate and manage devices, and optimizes network traffic flow. You successfully applied the right technical skills and demonstrated your ability to apply those skills thoughtfully. Summary and looking ahead. In this lesson, you learned about essential LAN technologies. Ethernet connects devices with physical cables, ensuring efficient data transfer through a star topology. Token ring, with its closed-loop network, minimizes data collisions, but tends to be slower than Ethernet. FDDI uses fiber optic cables for high-speed data transmission, featuring a dual-ring topology for added reliability. Finally, you learned how IP addressing, DHCP, APIPA, and IP reservations are vital components of LAN configuration and maintenance, ensuring effective communication within networks. The next lesson covers WAN technologies that are essential for connecting remote locations and optimizing network performance over long distances. You'll explore their features, benefits, and common techniques for optimization to meet specific network requirements. About this lesson, WAN protocols. With their vast networks spanning across continents, wide area networks, WANs, enable global communication. They are a testament to humanity's ability to bridge geographical gaps and foster worldwide connectivity. In this lesson, you'll explore WANs and their components. You'll learn about WAN fundamentals and their real-world applications. You'll learn how WANs differ from local area networks, LANs, discover the importance of encapsulation and multiplexing in data transmission, and compare three common WAN technologies: point-to-point protocol, PPP, multi-protocol label switching, MPLS, and frame relay. An introduction to WAN technologies. The most common example of a WAN is the Internet. The Internet is an open network, meaning anyone can use it. Other WANs are closed networks and require special permissions to access them. A business, for example, can build a WAN that is a closed network to connect offices in 2 or more cities. What makes both types of networks WANs is that they are networks that cover large distances. Computer monitors circling the world with signals emitting from the globe. Like LANs, WANs use protocols to set the rules that data must follow to get from the source to the destination. WAN protocols differ from LAN protocols in a variety of ways. The rules that govern data transmission over large areas and possibly open networks must be broader to account for the variety of circumstances in which the data can be found. Select each tab to learn more about ways WAN protocols differ from LAN protocols. Complexity. WAN protocols must be equipped to handle potentially more complex routing, while LAN protocols can be simpler because they operate within the same network, usually over a short distance. WANs must navigate a variety of network devices like routers, switches, and firewalls, each with its own configurations. This makes WANs inherently more complex to manage than LANs, which usually involve fewer devices and simpler configurations. Latency. WAN protocols must adjust for speed and latency challenges that can occur over long distances. WAN protocols must manage more hops between different types of hardware over greater distances, which can slow things down. LANs have fewer devices and shorter cable lengths, making them more direct and faster. Reliability. WANs are more susceptible to outages due to their complexity and the larger number of devices involved, so error correction mechanisms are often built into the protocols for reliability. LANs are more reliable, so they have error detection mechanisms and rely on higher-level protocols to provide error correction. Adaptability. WAN protocols must be adaptable to various data types and routes. LANs usually have a more predictable data flow, allowing for simpler protocol rules. Security. WANs are exposed to a broader set of risks, including interception and data loss over long distances. WAN protocols provide enhanced security measures, such as multi-factor authentication and advanced encryption, to protect against these risks. LANs usually are confined to a secured physical space and require less robust security measures. Now that you've learned about the differences between WAN and LAN protocols, let's explore two technologies to ensure data traveling through a WAN reaches its destination. Encapsulation and multiplexing in WAN technologies. Because data must travel farther and might encounter a variety of problematic circumstances, such as network congestion, hardware failures, or unauthorized access, that can reduce the data's integrity, engineers have developed technologies for ensuring data reaches its destination intact. Encapsulation and multiplexing are two of these technologies. Let's walk through a scenario to learn more. Imagine a large corporate campus that is experiencing significant issues with its WAN. The company's central network is failing, leading to widespread disruption across various office buildings. Samira, an experienced IT support technician, is tasked with resolving this urgent problem. A woman working with documents in front of a computer in a server room. In the Network Operations Center, Samira reviews the situation. Data packets are not reaching their intended destinations, causing delays and failures in communication. To address this, she decides to implement encapsulation. Encapsulation packages data with essential instructions before sending it over the network. This process involves enclosing each data packet in a layer of metadata to guide it through the network securely. The metadata serves as routing instructions, ensuring that each packet arrives at its destination without being compromised or lost. In a WAN, this packaging helps guide the data through a complex maze of interconnected systems. To set up encapsulation, Samira uses a centralized configuration management tool to set up encapsulation settings and push them to all the devices in the network. With encapsulation in place, the network exhibits signs of improvement. However, Samira recognizes that she needs to address a second issue: bandwidth inefficiency. The network is like a single road on which various vehicles, cars, trucks, and motorcycles compete for space. The need for a more organized system is evident. Samira then configures the network for multiplexing. Multiplexing is a technique that lets various signals use the same communication channel at once. Configuring a network using multiplexing allows multiple types of data to share a single channel by assigning each a specific lane or time slot. In doing so, the network can efficiently handle different data types simultaneously, making optimal use of the available bandwidth. In WANs, an engineer can configure multiplexing to run different services, such as internet, video, and voice calls, through one single physical connection. After carefully monitoring the results, Samira observes that the network's performance has stabilized. Data packets are reaching their destinations as intended, and the network is utilizing bandwidth more efficiently. Her expert use of encapsulation and multiplexing has successfully restored the integrity of the network, allowing the corporate campus to resume their normal activities. Exploring WAN technologies. WAN technologies enable large networks used in big corporations or as large as the Internet to send and receive data efficiently, reliably, and securely. WANs make it possible for data to navigate its way over a variety of different hardware and environments. Let's examine the following WAN technologies. Point-to-point protocol, PPP. Multi-protocol label switching, MPLS. Frame relay. Point-to-point protocol, PPP. Introduced in the early 1990s, point-to-point protocol, PPP, quickly became instrumental in bridging the gap between local computing environments and the broader Internet, serving as a go-between for devices, such as personal computers and larger Internet service providers. While other more modern technologies have emerged, PPP continues to be relevant and widely implemented, particularly for mobile Internet access and residential broadband services. PPP is a protocol used for establishing a direct connection between two network nodes. It facilitates the transmission of data packets over a simple, point-to-point link. Because of its focus on simplicity and efficiency, PPP is often the technology of choice for temporary or short-term network setups. It has also evolved to include security and data optimization features, making it suitable for a range of applications, from basic Internet browsing to more secure, though smaller scale, enterprise connections. Notice in the diagram below that a PPP is for a simple network connection between two devices. The line represents a network cable and the PPP protocol ensures data can be transmitted and received between the two devices. An illustration of a PPP network that shows two routers connected by a direct link represented by a red line between them. What do IT support technicians need to keep in mind? While PPP might not be the newest technology available, it remains widely used, especially in mobile Internet and some residential broadband settings. IT support technicians should be well versed in PPP, as they might encounter it in various network configurations. For instance, many remote or temporary work sites still use PPP for establishing quick and secure Internet connections. Technicians might also run into PPP when dealing with legacy systems that haven't been updated to newer technologies. Understanding PPP is essential for troubleshooting issues related to Internet connectivity and for ensuring secure and efficient data transmission. Additionally, IT support technicians might have to configure PPP settings for specialized network requirements or to maintain compatibility in hybrid environments that use both older and newer technologies. Select each section to learn more about the features of PPP. What it does. PPP is a way to link two devices directly, like connecting your computer to the Internet through a service provider. Think of it as a private chat between just two people. It's often used for mobile Internet and home broadband services. How it works. PPP connects the two network nodes using a cable. To send data, PPP sets up a direct link by setting some parameters to ensure both devices understand each other and agree on how to exchange information. Once they're on the same page, data starts flowing back and forth between them. It's kind of like shaking hands before starting a conversation. Topology. PPP topology is straightforward. It connects one device directly to another, such as a straight line between 2 points. This makes it simple to manage but means it's best for situations where you only need to connect two devices, not a whole network of them. Speed. PPP isn't necessarily the fastest way to transfer data, but it's usually fast enough for common uses, such as internet browsing or streaming. The actual speed can vary based on what kind of cables or other technology you're using. How it's unique. What makes PPP stand out is its simplicity and efficiency. It's easy to set up, making it great for short-term needs like connecting to the internet through a phone line. Even though it's simple, it still offers ways to keep your data secure and transfer it quickly. Multi-protocol label switching, MPLS. Multi-protocol label switching, MPLS, is a key tool for making WAN networks run smoothly. Think of it as the GPS system for internet traffic. Just like GPS helps your car find the best path to reach a destination, MPLS helps data find the quickest route through a network. It's popular in large businesses and internet service providers because it helps data move quickly and efficiently. Instead of using long, complicated addresses to move data, MPLS uses short labels. This speeds up the process and makes everything work more efficiently, especially for services that need data to move in real time, such as video calls or streaming services. Notice in the following diagram how all network connections, represented by lines, go through the MPLS system. MPLS connects the remote sites and workers to the router and firewall of the main office, which then connects to the internet represented by a cloud. An illustration of a MPLS network represented as a cloud and various devices and sites connected to each other through the MPLS network. MPLS is represented as a cloud and various devices and sites connected to each other through the MPLS network. The internet is represented as another cloud. All sites, devices, and clouds are connected by lines representing network connections. What do IT support technicians need to keep in mind? MPLS is crucial for ensuring efficient data travel in WAN networks. IT support technicians must be equipped with a robust understanding of its operations. Large businesses and internet service providers rely on MPLS for its efficiency. By understanding its configuration, IT support technicians can better troubleshoot and optimize a network that uses the technology. To ensure seamless and real-time data transfers, such as during video conferences or streaming, technicians need to understand how MPLS uses concise labels in place of lengthy addresses for data routing. Moreover, with businesses relying heavily on real-time services, IT support technicians play a crucial role in ensuring that MPLS configurations are optimized and any issues are promptly addressed to minimize disruptions. Select each section to learn more about the features of the MPLS protocol. What it does. MPLS acts like a traffic manager for data traveling over a network. Imagine it as a virtual signpost that guides data packets to their destination along the most efficient route. This is especially useful for businesses and service providers who need to move a lot of data reliably and quickly. How it works. Instead of using long and complex network addresses, MPLS assigns short labels to data packets. It's like giving each packet a quick and easy-to-read name tag. This simplifies the routing process and helps data reach its destination more quickly, with fewer roadblocks. Topology. MPLS is quite versatile, working well in simple setups, such as a direct connection between two locations, as well as in more complex network architectures. This adaptability makes it suitable for a wide range of networking needs, from basic to complex. Speed. The speed of a network using MPLS technology isn't determined by the MPLS technology itself but rather by the underlying physical infrastructure. MLPS streamlines the process of moving data, making data transmission more efficient. How it's unique. What sets MPLS apart from other ways to manage network traffic is its mix of speed, reliability, and flexibility. It's good at adapting to different kinds of data and network setups. It's a strong choice for situations requiring stable and fast data movement, such as real-time voice or video services. Frame relay. Frame relay is a type of wide area network, WAN, protocol that enables the transmission of variable-sized data packets, called frames, over a network. Emerging in the late 1980s and 1990s as an evolution from earlier packet switch technologies, frame relay was designed to make more efficient use of existing physical network infrastructures, allowing for quicker data transfers compared to older systems. The main advantage of frame relay is its simplicity and efficiency. By using a simplified addressing scheme and discarding error-prone packets, leaving error correction to end devices, it streamlines the process of data transmission. As a result, it was often used for connecting corporate branch offices and data centers over long distances. Though newer technologies like MPLS have largely replaced frame relay in many applications due to its enhanced flexibility and performance, frame relay remains an important historical stepping stone in the evolution of WAN technologies and is still in use in certain legacy systems and niche scenarios. What do IT support technicians need to keep in mind? Understanding frame relay is still important for IT support technicians, even if newer technologies have come to the forefront. There are instances where technicians might encounter legacy systems in businesses or older infrastructure that rely on frame relay. Being familiar with how frame relay operates and how to troubleshoot it ensures that data continues to flow smoothly, especially in environments that might mix both old and new technologies. Additionally, some businesses might be slow to transition away from frame relay due to its reliability or specific use cases. As a technician, it's crucial to know how to configure, maintain, and support these systems to ensure consistent and efficient network performance. Select each tab to learn more about the features of the frame relay protocol. What it does. Frame relay is a technology primarily used for linking local area networks over a broader geographic range. Although it's considered an older technology, it remains in operation due to its specific utility and cost-effectiveness. How it works. The frame relay protocol takes data originating from one local area network and routes it to a designated point within another, often distant, local area network. It does so by encapsulating the data in a specialized format suited for this type of long-distance communication. The technology is straightforward, although it lacks some of the advanced features found in newer protocols. Topology. The topology of frame relay is flexible, as it can support connections between multiple points. This makes it adaptable for various networking requirements, albeit with limitations in speed and reliability relative to more modern solutions. Speed. In terms of data transfer rates, frame relay is generally slower compared to contemporary technologies. While not suitable for tasks requiring high-speed data transfer or real-time applications, such as video conferencing, it is usable for less demanding use cases. How it's unique. Frame relay is noted for its cost-effectiveness, presenting an economical option for network connectivity. However, this affordability comes at the expense of speed and reliability, making it less suitable for applications requiring high performance and robustness. The diagram below illustrates how a frame relay network works. Notice that the frame relay switches are in a cloud, which indicates that the specific path data might take through the network might travel to one or more of the switches. The network traffic is then sent to various routers in remote locations indicated by the lines that connect the switches to the routers. Practical application of WAN technologies for network configuration and optimization. WANs present network engineers with special problems to solve. Unlike smaller networks that cover just a building or campus, WANs can connect places as far apart as different cities or countries. Data transfer over a WAN will go through many kinds of equipment and situations. These situations include things such as interference, data getting lost, and even the effects of weather. While smaller networks also face some of these issues, WANs are more likely to be affected by them. The work of designing and setting up a WAN typically is the responsibility of a network engineer or network architect. Even so, IT support technicians are responsible for maintaining and troubleshooting these networks. So, first-hand knowledge of how network engineers design and implement a WAN is essential for the IT support technician to be effective in their role. Select each tab to learn more about the challenges data faces when traveling over a WAN. Equipment variability. In a WAN, data passes through many types of equipment, such as switches and routers. These devices can differ in age and setup, creating potential slowdowns. Optimizing these varying pieces of equipment ensures a quicker and smoother flow of data. Signal strength challenges. The farther that data needs to travel, the weaker the signal can become. This is especially a problem in WANs, which can use a mix of different types of cables or even satellite connections. Employing strategies to strengthen the signal or correct errors helps maintain a reliable network. Interruptions and lost data risks. Data traveling over a WAN often shares channels with other types of signals. This shared usage can lead to lost or delayed data. Implementing techniques to prioritize important data ensures it reaches its destination even when the network is busy. Traffic congestion. WANs can experience slowdowns due to heavy data traffic, much like a road gets congested during rush hour. Methods to manage this traffic might include prioritizing more critical data, allowing it to move through the network more efficiently. Because of these challenges, network engineers have developed techniques for using various WAN protocols strategically to optimize WAN performance. An understanding of these WAN challenges and optimization techniques equips IT support technicians with the skills needed to maintain network health, improve performance, and troubleshoot network issues more efficiently. Using PPP for simple networking. You've learned how PPP networks work and the role they play in a variety of networking options. Let's explore PPP networks further by following Adrian as he sets up a PPP network to better connect two remote locations for his company. Adrian, a network engineer, needs to establish a secure and efficient data connection between the main office and a remote field office of his company. The main office houses sensitive data that needs to be accessible to team members at the remote location. However, the field office is in an area with limited network infrastructure, requiring a solution that uses minimal bandwidth. A man working on a computer in a server room. After considering various options, Adrian chooses to implement a PPP connection between the two locations. PPP offers minimal protocol overhead, making the most of the limited bandwidth available at the field office. Furthermore, PPP's capabilities for encryption and authentication provide the level of security needed for the sensitive data being shared. Additionally, the dynamic nature of the field office, with different teams coming in and out, calls for a flexible addressing system. PPP's ability to provide dynamic address assignment allows Adrian to effortlessly manage the variable environment at the field office. By selecting PPP, Adrian successfully establishes a secure, efficient, and adaptable connection tailored to the specific needs of his organization. Now that Adrian has implemented a PPP connection between the two locations, there are a few techniques he can use to optimize the network to avoid future potential problems. Many of these optimization techniques are features of PPP that network engineers or IT support technicians can enable on PPP-based networks. Let's learn about the common techniques for optimizing PPP networks. Enabling compression. Enabling compression settings reduces the amount of data being sent over the connection, thereby increasing speed. Implement quality of service, QoS. Implementing QoS can ensure that the most critical data gets the fastest service by prioritizing certain types of traffic. QoS is a set of rules that prioritize different types of data traffic to ensure optimal performance and reliability. Configure multi-link PPP, MLPPP. MLPPP is bundling multiple physical links into a single logical data connection, the point-to-point, in cases where a network needs higher bandwidth. It's like sending a card and addressing it to a family. The family is one thing that represents multiple people. Each family member will be able to read the card even though you sent it to a single recipient. This not only increases the available bandwidth but also provides redundancy. Monitor quality of the data connection. Monitoring the quality of the data connection can alert network engineers or IT support technicians to any deteriorating conditions, allowing them to take action before problems become more severe. Enable keep alive messages. Keep alive messages allow PPP networks to check and maintain the status of the link. If a link is idle, but still active, the network sends small messages to keep the connection open. This avoids the overhead of having to re-establish the connection, saving both time and resources. It's like being put on hold with customer service rather than having to get a call back each time the service person has new information. Using MPLS for reliable communication. You learned that MPLS helps data find its way to its destination more efficiently. In the following scenario, Artie, a network engineer, implements MPLS to improve network bandwidth. Learn how MPLS can improve network performance by exploring how Artie uses this technology in her healthcare organization's network. Artie is a network engineer responsible for improving the WAN for a healthcare organization that has multiple clinics and hospitals across several cities. The organization is looking for a way to transmit patient records and medical images between these locations quickly and securely, all while keeping an eye on the budget. A woman typing on a laptop in a shared working space. In this situation, Artie decides to implement MPLS as the technology to enhance the WAN. MPLS is known for its efficiency in directing data packets along the best possible paths, effectively acting like a virtual signpost for network traffic. This makes it a good fit for the healthcare provider's need for speed and reliability, especially for critical applications, such as real-time access to medical records. By simplifying the routing process using short labels, MPLS allows for more efficient use of bandwidth. This means the healthcare organization can handle more data without needing to invest in a major network upgrade. Additionally, MPLS offers robust security features, ensuring that sensitive patient data is transmitted securely between locations. This is a significant benefit for a healthcare provider dealing with confidential information. In the network security and privacy discipline, confidential information is also called personally identifiable information, PII. PII is legally protected in many countries and can include things like home addresses, bank account records, employment information, passport number, and health information. Anything that can be used to identify an individual is considered PII and should be treated as confidential. By implementing MPLS, Artie can improve the way patient records and medical images are transmitted between locations. Now that Artie has implemented MPLS, there are a few techniques she can use to optimize the network to avoid future potential problems. Let's learn about the common techniques for optimizing a network with MPLS. Configure label switching. Configuring MPLS to use label switching streamlines the routing process. By attaching labels to data packets, they can ensure that data takes the most efficient route, ultimately speeding up network performance. Engineer network traffic. Engineering network traffic allows network engineers to design a network where data flows efficiently, minimizes bottlenecks, and makes the best use of available bandwidth. Depending on their needs, they can manually or automatically set the paths that data packets should follow. Configure quality of service, QoS. Quality of service, QoS, settings allow network engineers to prioritize different types of traffic. For instance, they can allocate more resources to time-sensitive data, such as video or voice calls, ensuring these services run smoothly. Enable fast reroute. Enabling the fast reroute feature in MPLS configurations allows the network to quickly switch to an alternate path in the event of a failure or bottleneck. The fast reroute feature keeps data flowing smoothly with minimal disruption. Many of these optimization techniques are features of MPLS that network engineers can enable when using MPLS on a network. Leveraging frame relay for cost effectiveness. Some engineers might choose frame relay technology mainly because it's less expensive to use than other technologies. In the following scenario, you'll learn that cost isn't the only factor for choosing frame relay. Not only is frame relay cost effective, but it also can meet the needs of businesses that rely on their WAN to get work done. Follow along as a network engineer. Prescott implements frame relay to improve his company's network and stay within budget. Prescott is a network engineer faced with a complex challenge. He's responsible for the network infrastructure of a mid-sized retail company with multiple stores spread across the state. The company's management has approached him with a pressing issue: they need a reliable, scalable, and cost-effective network that can handle diverse data traffic needs for each location. Some branches require frequent data transfers to and from the central inventory database, while others need only periodic updates. All of this must be achieved within the constraints of a tight budget. Man working behind several workstations in a big control room. Adding to the complexity, the company has an existing investment in frame relay technology, a setup that was put in place years ago. Upgrading to a newer network technology would be costly, requiring not just financial resources but also time for a complete system overhaul. The management tasks Prescott with evaluating whether the company's existing frame relay setup can be optimized to meet its current network needs. After thorough analysis, Prescott decides that frame relay is indeed up to the task despite being an older technology. Its scalability allows him to connect all the branches to the central database without installing new, costly, dedicated lines. Furthermore, frame relay's flexibility in handling various types of data traffic means he can prioritize crucial data while accommodating the specific needs of each location. By choosing to optimize the existing frame relay network, Prescott successfully meets all the company's requirements. He not only creates a unified, efficient network for the various branches but also shows fiscal responsibility by leveraging the existing technology, thus avoiding an expensive overhaul. There are a few techniques Prescott can use while optimizing the existing network. Many of these optimization techniques are features of frame relay that network engineers or IT support technicians can enable when optimizing networks using frame relay technology. Let's learn about the common techniques for optimizing frame relay technology. Enable traffic shaping. Traffic shaping can ensure that the most important data, such as inventory updates, gets priority over less urgent traffic. This way, essential tasks are completed on time, making the network more efficient. Imagine a busy highway where emergency vehicles need to get through quickly. Traffic shaping is like setting up special fast lanes for these vehicles. Monitor Local Management Interface, LMI. Local Management Interface, LMI, are signals sent out by frame relay devices that provides network engineers with up-to-the-minute information on how the network is performing. If there's a bottleneck or a failure, the engineer can take immediate action to solve the problem. Configure fragmentation. Configuring fragmentation breaks down large data packets into smaller, more manageable pieces. In a frame relay network, big chunks of data can cause delays. Fragmentation allows for quicker and more efficient data transmission, just as smaller vehicles move more easily through traffic. Set up Committed Information Rate, CIR. Committed Information Rate, CIR, is a type of quality of service measure that ensures that a certain amount of bandwidth is always available for data. It is achieved through a combination of settings, traffic policing mechanisms, and network management protocols. Network engineers can set these limits to make sure critical tasks always have the resources they need. Summary and looking ahead. In this lesson, you learned about WAN protocols and their characteristics. WANs cover large distances and make the internet possible. They need special protocols for longer distances, speed, accuracy, adaptability, and security. You learned about the characteristics of WAN protocols, including PPP, MPLS, and frame relay. Finally, you learned various optimization techniques to enhance the performance of these WAN protocols. The next lesson covers Internet protocols and their roles in web communication. About this lesson, Internet communication protocols. Have you ever wondered how the Internet seamlessly connects you with people across the globe through voice calls, video conferences, and emails? In this lesson, you will learn about Internet protocols and their essential roles in web and email communication. You'll discover different types of Internet-based communication tools, such as VoIP, text messaging, video conferencing, and more. Additionally, you'll explore the protocols that enable communication tools and email communication, including their benefits and limitations, so you have a comprehensive understanding of Internet-based communication technologies. Internet communication tools and the protocols that power them. While LANs are critical for businesses and home users alike, the WAN of the Internet has enabled scenarios that early developers of network technology never thought of. These scenarios range from streaming movies in your home to delivering data to support the largest business projects. The Internet also has changed the way people communicate. For business professionals, email has become a go-to method of communication, even more so than traditional phone calls. Even the way phone calls are made has changed, thanks to digital technologies. People working on computers in a co-working space. For example, Voice over IP, VoIP, is an increasingly popular option that lets people make voice calls using the Internet instead of traditional phone lines. Voice over Internet Protocol, VoIP, uses network protocols, such as Session Initiation Protocol, SIP, and Real-Time Transport Protocol, RTP, to convert voice information into data packets. These packets are then transmitted over the Internet and reassembled at the other end for clear, real-time communication. This process bypasses traditional telephone lines, relying instead on Internet-based technology. VoIP is one of the many ways people communicate with each other using Internet technology. People also use text messaging and social media to send direct messages to an individual or groups. Many professionals use video conferencing tools to hold business meetings, and individuals use them to keep in touch with family in distant locations. Internet-based communication tools. The spectrum of Internet-based communication tools represents a diverse and continually evolving technological landscape. Some of these tools are engineered for peer-to-peer communication, while others are scaled to facilitate communication with large audiences. Still others are specialized for business environments. Select each card to learn more about the range of Internet-based communication tools. VoIP services have transformed traditional voice communication by allowing calls to be made over the Internet. Examples: Skype, Zoom, Vonage. Text messaging services facilitate quick and simple text-based communication between users. Examples: WhatsApp, SMS, iMessage. Video conferencing tools have become crucial for remote work, virtual meetings, and even social gatherings. Examples: Zoom, Microsoft Teams, Skype, Google Meet. Collaboration software provide individuals within a team or organization with a unified digital environment where they can effectively communicate, share information, and work together on projects, regardless of their physical locations. Examples: Slack, Asana, Trello. Online forums and message boards allow for community-based discussions and Q&As. Examples: Reddit, Quora. While traditional blog platforms might not seem like two-way communication platforms, the comment sections often serve as a venue for readers to interact with authors and each other. Examples: WordPress, Medium. Streaming services allows users to consume live broadcasts or recorded content and often include chat features for real-time viewer-to-viewer interaction. Examples: Twitch, YouTube Live. Customer support software uses chat or ticket systems to enable customer service communications. Examples: Intercom, Zendesk. Virtual reality platforms offer a more immersive form of communication, often using proprietary protocols for data transmission and rendering. Examples: Oculus Rooms, ArtSpace. IT support technicians are often the first point of contact for resolving issues related to Internet-based communication tools, such as VoIP or video conferencing platforms. Having a deep understanding of how these tools interact with the network can speed up troubleshooting. Also, Internet-based communication tools often require specific network configurations to function optimally. IT support technicians must understand how to prioritize traffic to ensure high-quality calls and meetings. What do you think? Employability skills. Critical thinking. What internet-based communication tools do you use in your personal or work life and for what purposes? Evaluate your thinking. Does your answer account for the following? Some tools you might use in both your work and personal life. You might send a text message to friends to organize a dinner and also share your phone number with coworkers so you can quickly exchange information or get alerted to issues wherever you are. Many internet-based tools, like Google and Microsoft tools, support switching between user accounts easily, so you can use the same tool in different environments. You might use Google Meet to video conference with coworkers and then, by switching the logged-in account to a personal account, you can use the same tool to set up a call for your child with their grandparents. Many times, this can be done very quickly by just adding and then selecting a second account. You've learned there are many different types of internet-based communication tools. Each of these tools requires special technologies to support data transmission over WAN networks. Internet protocols that power communication tools. At the heart of these tools are protocols that make communication possible. The engineers who create these tools choose or create the protocols they'll use based on what data the tool needs to transmit and other factors of the transmission, such as speed. For example, if users of a VoIP tool experience any lag in the transmission of their voice to the recipient, the people on the call can talk over each other, which can result in frustration. A VoIP protocol must ensure that the data is transmitted in as close to real time as possible. The protocol an engineer needs for a text messaging app might not be so stringent. Like most technology, every protocol has costs and benefits. When choosing which protocols to use, engineers must weigh the costs and benefits against the user's needs and the goals the tools are meant to accomplish. Let's learn about which protocols are used for which tools and their advantages and limitations. Session Initiation Protocol, SIP. When to use, or use case VoIP, Customer Support Software. Description: SIP establishes the connection between VoIP calling parties. It's like a digital handshake that ensures both sides are ready to start a conversation. Advantages: SIP supports a wide range of media types, including voice, video, and instant messaging. This enables more versatile and unified communication experiences. Limitations: it is difficult to set up. Getting it to work can be a bit complicated, like putting together a puzzle. SIP might not work well with some computer or network security configurations. Real-time Transport Protocol, RTP. When to use, or use case VoIP. Description: once a VoIP conversation starts, RTP takes over. It's responsible for delivering audio and video packets in real time, allowing for seamless communication. Advantages: RTP is fast and immediate. RTP is all about speed, ensuring that voice or video doesn't lag or stutter during a VoIP call. Limitations: it needs a stable network. RTP can consume a lot of internet bandwidth. If the internet connection is slow, the call quality can suffer. It's not secure on its own. By itself, RTP doesn't have built-in security features, so extra measures are needed to keep the call secure. Short Message Peer-to-Peer Protocol, SMPP. When to use, or use case text messaging. Description: used primarily for small message service, SMS, services. SMPP allows for the transfer of short messages between devices, such as mobile phones and the SMS Center, SMSC. The SMSC is responsible for making sure that your message gets to the right person. It's like a post office for text messages. Advantages: SMPP can handle a large number of messages per second, which is great for bulk messaging. Limitations: it is limited to text. SMPP is mainly for text messages, so it's not ideal for sending other types of data, such as images or videos. SMPP is complex and technically taxing to set up. Extensible Messaging and Presence Protocol, XMPP. When to use, or use case text messaging. Description: popular in instant messaging apps, XMPP enables real-time text transmission and shows when a user is online. Advantages: XMPP is versatile and flexible. It can handle text, voice, video, and even presence information, like when someone is online. It is also open standard. This means that many different systems can use it, making it easier to integrate with other services. Limitations: XMPP is resource intensive. XMPP can be heavier on system resources, especially if engineers use it for more complex tasks, such as video chat. It can require additional configurations for security. While XMPP supports secure data transmission, it often needs extra setup to make sure user authentication is fully integrated with existing systems. Hypertext Transfer Protocol/Secure, HTTP/HTTPS. When to use, or use case collaboration software, online forums and message boards, customer support software. Description: HTTP/HTTPS are the backbone of web-based platforms, including social media sites. They handle the request and delivery of multimedia content, such as support tickets, text, images, and videos. Advantages: HTTP/HTTPS is easy to implement, it's widely supported, and secure, in the case of HTTPS. Limitations: this can be slower due to higher overhead, particularly with HTTPS, which involves encryption. Real-time Messaging Protocol, RTMP. When to use, or use case video conferencing tools, streaming services, blogging platforms. Description: RTMP enables sending video and audio over the internet, mainly for streaming. Advantages: RTMP has low latency. This means there's very little delay between the live event and what you see on your screen. It's high quality. RTMP can deliver high-quality video and audio streams. Limitations: RTMP requires a strong internet connection. Because it aims for high quality and low delay, RTMP can use a lot of internet bandwidth. It's also less efficient. Newer technologies can do the same job using less data, but RTMP is still widely used because it's well established. Many people use one or more of these communication tools each day. In addition to widely used communication methods such as VoIP, text messaging, and video conferencing, there's another tool that both individuals and business professionals use daily: email. Internet protocols for email. Email is widely used for digital communication, especially in the workplace. What sets email apart is its asynchronous nature. Asynchronous refers to events that do not occur at the same time or in a specific sequence. In communication, it means that the sender and receiver don't have to be available at the same time, allowing individuals to respond at their convenience rather than demanding immediate engagement. A man holding a tablet and working on a laptop. Email accommodates a wide array of supplementary technologies, enabling users to seamlessly incorporate voice recordings, documents, images, and videos within their messages. For many, email has assumed the role of a digital repository, protecting records of conversations, important details, and documents so they can be used again in the future. As with the other forms of digital communication, email uses a unique set of protocols. Let's learn more about email protocols and their benefits and limitations. Simple Mail Transfer Protocol, SMTP. When to use, or use case sending emails. Description: SMTP is the go-to protocol for sending emails from a client to a server or between servers. It acts like a postman, taking an email and making sure it gets to the recipient's mailbox. Advantages: SMTP is widely used and universally accepted. It's reliable for sending emails. Limitations: it's limited to sending emails, not receiving. It is not secure on its own, it requires additional configurations for encryption. Post Office Protocol 3, POP3. When to use, or use case receiving emails. Description: POP3 downloads emails from the server to a local device, essentially like receiving physical mail and storing it in a personal file cabinet. Advantages: POP3 enables a faster retrieval of new messages. It also saves server space. Limitations: POP3 is not ideal for multiple devices. Limited folder and flag management. Internet Mail Access Protocol, IMAP. When to use, or use case receiving emails. Description: IMAP allows email clients to view and manage messages online as if they were stored locally in desktop and mobile clients. It's like having a window to an online mailbox, showing all the online emails in real time. Advantages: IMAP syncs across multiple devices. It allows folder and flag management. Limitations: emails take up more server space and IMAP is slower than POP3 for some operations. Transport Layer Security / Secure Sockets Layer, TLS / SSL. When to use, or use case email security. Description: these protocols add a layer of security to email transmissions. Think of them as the seal on a confidential document envelope. Advantages: TLS / SSL encrypts email content during transmission. It enhances overall email security. Limitations: TLS / SSL adds complexity to the email setup. It can slow down the sending and receiving process slightly. Activity: troubleshoot internet communication tools and internet protocols. Employability skills. Critical thinking, communication. In this activity, you'll learn about troubleshooting internet connection tools and internet protocols. You'll read the following scenarios about Rhett, who is an IT support technician having a challenging day troubleshooting multiple communication tools for his colleagues. You'll then reflect by answering some questions about how Rhett could have more effectively worked to troubleshoot the issues. Introduction. Man sitting at desk in a small office looking at computer screen with some code on it. Rhett provides IT support in a fast-paced financial services company. Tasked with ensuring seamless communication and system reliability, he's known for his quick responses and can-do attitude. Today, Rhett finds himself grappling with multiple issues affecting the company's communication tools. Scenario 1. VoIP. The challenges. The morning starts off on a difficult note. Rhett's Slack is pinging non-stop, with employees across different departments complaining about the poor quality of the VoIP calls. Words are garbled, calls are dropping, and in some instances, connections cannot even be established. Given that the VoIP system is integral for both internal meetings and client consultations, this is a significant problem. Rhett's VoIP tool troubleshooting. Rhett, keen to resolve the issue, focuses in on what he believes could be the problem. Due to the fact that the VoIP calls are dropping, Rhett believes that there might be data congestion affecting the VoIP system. He takes the following steps to adjust the SMTP settings by accessing the client admin interface in a web app and ensure the STMP server address and port numbers are correct. Adjust some of the security protocols, like SSL/TLS. Scenario 2. Collaboration tools. The issues. Just as Rhett is wondering why the VoIP issues continue despite his efforts, a fresh wave of complaints rolls in. This time, employees are frustrated with the company's proprietary collaboration tools and customer support software. Employees are unable to access important customer support tickets and documents that they've been working on collaboratively with colleagues. Rhett's collaboration tool troubleshooting. Realizing the severity of the situation, Rhett believes there might be an issue with the HTTPS protocol settings. He believes that the security settings, like rate limiting, might be too stringent and are blocking some features. After Rhett carefully checks and optimizes the HTTPS protocols, the collaboration tools and customer support software are back on track, much to everyone's relief. Scenario 3. Email. The problems. During his afternoon coffee, just when Rhett thinks he can focus on the problems he's already received, he gets another batch of tickets from his co-workers. Company emails are either bouncing back or not being sent at all, causing internal and external communications to grind to a halt. Rhett's email troubleshooting. Knowing how critical email is for business functions, Rhett gets back to his desk. He wonders if the SMPP protocol has been incorrectly configured, causing authentication errors and preventing users from sending emails. He also thinks that maybe the XMPP protocol has timed out, causing issues. He reviews the settings for SMPP and XMPP, and makes a few adjustments. During testing though, he determines this has, unfortunately, not fixed the email issues. Summary. As the workday winds down, Rhett reviews his actions and their outcomes. He's managed to restore functionality to the collaboration tools and customer support software, a definite win. However, there are still persistent issues with the VoIP and email systems. Rhett has the feeling he might have missed something crucial for these unresolved issues. What do you think? Employability skills. Critical thinking. Answer a few questions to help Rhett more effectively to troubleshoot these internet-based communication tool issues the finance company was facing. Evaluate your thinking. Does your answer account for the following? In the first scenario, while troubleshooting VoIP issues, Rhett should have focused on the Session Initiation Protocol, SIP, and Real-Time Transport Protocol, RTP, which are two protocols that enable VoIP communication tools. In the second scenario, the role of HTTPS protocol for internet-based communication tools is to handle the request and delivery of multimedia content, such as support tickets, text, images, and videos. In the third scenario, instead of focusing on SMPP and XMPP protocols that enable text messaging, Rhett should have focused on SMTP that enables email sends, IMAP and POP3 for receiving emails, and TLS/SSL that provides email security. Summary and looking ahead. In this lesson, you learned about the role of Internet protocols in shaping modern communication. You explored how these protocols facilitate web and email communication, enabling a wide array of Internet-based tools and services. Specifically, you learned about the common Internet-based communication tools that people use every day. And you explored the Internet protocols that power communication tools and email. The next lesson covers network services and protocols, including Network Time Protocol, NTP, for time synchronization, Domain Name System, DNS, for domain-to-IP resolution, and Dynamic Host Configuration Protocol, DHCP, for IP address management. You'll learn how these protocols work together and their roles in network operations. About this lesson, network services. In this lesson, you will explore the critical components that support the functionality of the Internet. You'll learn about the pivotal role played by the Domain Name System, DNS, and how it facilitates the transformation of user-friendly domain names, such as www.ibm.com, into the numerical IP addresses that computers rely upon. You'll learn about precise timekeeping through the Network Time Protocol, NTP, and its importance across various sectors. Furthermore, you'll learn how the Dynamic Host Configuration Protocol, DHCP, simplifies the allocation of IP addresses. Finally, you will learn how all these protocols work together on a network. The directory of the Internet. You've learned what IP addresses are and how IP addresses are assigned and managed. An IPv4 address, the most common IP address, has a very specific structure. It consists of 4 sets of numbers separated by a period or dot. Recall that each set is called an octet and range from 0 to 255. There are 2 key parts of this example IP address, 192.168.1.1. In the IP address 192.168.1.1, the first 3 octets, 192.168.1, represent the network address. The first part of the IP address is called the network address. In the IP address 192.168.1.1, The portion 1.1 represents the host ID. The second part of the IP address is called the host ID. While networks might know what to do with the set of numbers that make up IP addresses, to humans, it doesn't mean much. Every device or resource on the internet is located by an IP address. Imagine how inconvenient it would be if, to visit your favorite social media site, you had to memorize its IP address and type that in your browser. It's similar to having to remember a friend's phone number every time you want to call them, instead of simply selecting their name from your contacts. You might wonder how a browser knows which IP address is associated with a specific domain name. Let's find out next. Introduction to the Domain Name System, DNS. One technology that makes the Internet more user-friendly is the Domain Name System, DNS. The DNS is a directory technology that matches domain names with IP addresses. Review the following animation to get familiar with how DNS works to find the right address. When the user provides a web address in their browser, the DNS server receives a request, resolves the IP address, and routes the request to the target web servers. The web servers send the web page to the user's browser. An animation showing a laptop screen displaying http://www.ibm.com. The URL goes to a DNS server that reads it as 94.245.11.67. The DNS server sends the request to IBM web servers. The web servers send the IBM web page to the laptop. Domain names enable you to find places on the internet using friendly natural language names. Consider a domain name, such as www.ibm.com. This address identifies 3 domains separated by the dots. The label .com signifies the top-level domain and is one that many addresses share. The second section, IBM, is considered a subdomain of .com. The combination of the subdomain IBM with .com creates a unique domain name since only IBM, the company, can use it. The third section, www, is another label and is a subdomain of ibm.com. A host name refers to domains combined with subdomains that have an IP address associated with them. Domain name, a domain name refers to the location of a website on the internet. Host name, a host name is the name of the device on the network. You can think of the system as street addresses in a city. Suppose a friend tells you they live at 123 Cactus Avenue. Avenue can be likened to a top-level domain, like .com and .net. It's a broad category that many addresses share. Cactus could be likened to the domain name, representing a specific location or entity within that category. 123 might be more akin to a subdirectory or specific page on a website, narrowing down the exact location further. So, combining 123, Cactus, and Avenue pinpoints a unique location in the city, just as combining a subdirectory, domain name, and top-level domain specifies a unique web address. While the city might also have a Cactus Lane or a Cactus Boulevard, there can be only one Cactus Avenue in a particular city, which also is a domain. If your friend's house was the only one on Cactus Avenue, they might just say they live on Cactus Avenue. But, because there are other houses on that street, they say they live at 123 Cactus Avenue. The DNS functions like the phone book of the internet. Just as you'd look up a friend's name in your phone book to find their number, the DNS keeps track of which host names correspond to which IP addresses. When you type a host name into your browser, it's akin to selecting a friend's name from your contacts. The DNS tells your browser the phone number, or IP address, to dial. Thanks to all the networking technology working behind the scenes, you're then connected to the website you intended, much like calling your friend after selecting their name. Common domain types and their meanings. Are you familiar with these common domain types? Take a moment to review the following table. The domain type .com means company. The domain type .net means network. The domain type .edu means education. The domain type .org means organization. The domain type .gov means government. The domain type .info means information. Troubleshooting and maintaining DNS. An IT support technician plays a crucial role in ensuring that the DNS functions smoothly. One of the first steps in troubleshooting a DNS issue is to check if the DNS server addresses are correctly configured on the network devices. IT support technicians might also need to clear the DNS cache. The DNS cache is temporary storage that holds the translations of recent domain names. This helps in resolving any outdated or incorrect translations. Additionally, technicians monitor the overall health of the DNS server, ensuring it's responding to requests, and they might perform regular updates to keep the system secure and efficient. For ongoing maintenance for a healthy DNS, IT support technicians regularly monitor the DNS server's performance and security. They look out for any unusual traffic patterns that might indicate an external threat. Backup routines are established to save DNS configurations and data. This ensures that in case of any system failures, the DNS can be restored quickly to minimize disruptions. NTP as an IP for clock synchronization. You might glance at a clock or watch or look at your phone to know the exact time. But have you ever wondered how computers and servers on a network keep their clocks in sync? Network Time Protocol, NTP, is an essential, but often unnoticed part of computing. It plays a critical role in making sure the clocks of devices on a network are in sync. NTP is a network protocol, a system of rules for transmitting data across networks. It's specifically designed to keep the internal clocks of computers synchronized. Having a uniform time across systems is vital for many functions, such as data logging, transaction processing, and secure communications. How NTP works: a hierarchical structure. Accurate timekeeping is crucial in many areas. For example, in financial markets, even a small discrepancy in time can impact transactions. In healthcare, medical equipment must accurately log data based on time. Many systems rely on precise timekeeping for their operations to run smoothly. To make sure that all networks and devices have accurate time, NTP follows a step-by-step structure. The best clocks set the standard time, and then NTP distributes this accurate time to all the networks and devices that use it. So, how does NTP work? Stratum levels. NTP organizes time servers into levels known as stratum. At the top are stratum 0 devices, which include highly accurate clocks, such as atomic clocks. Stratum 1 servers connect directly to these high-precision clocks and then distribute this time to other, lower-level servers and devices. Polling for time. Periodically, a device will ask, or poll, an NTP server for the current time. When it gets this time, the device calculates how much its internal clock differs from the server's time. This difference is the offset. Adjusting the clock. After calculating the offset, the device adjusts its internal clock to minimize this difference, thereby synchronizing its time with the server's time. Considering delays. NTP also measures the time it takes for data to travel between the client and server, known as round-trip delay. This delay is factored into the time adjustment to make it even more accurate. Multiple time sources. For added reliability, NTP uses more than one time source. It usually asks multiple servers for the time and uses special calculations to figure out the most accurate source. NTP is a vital part of network architecture that ensures accurate timekeeping across devices. By using a hierarchical model, calculating time differences, and factoring in network delays, NTP allows for a harmonized and accurate sense of time across networks. Troubleshooting and maintaining NTP on a network. An IT support technician must ensure NTP networks are functioning properly. If devices start showing inconsistent times, the IT support technician can first verify that the devices are correctly configured to communicate with the NTP server. Occasionally, the time data stored on a device might become outdated or corrupted, so the technician might reset it to sync with the NTP server. In situations where a corporation maintains its own NTP server, monitoring the server's health is vital to ensure it's accurately distributing time data to the network's devices. Continuous maintenance is key to a well-functioning NTP system. IT support technicians must be vigilant about the performance and security of the NTP server, ensuring it's safe from potential threats. For example, they might protect the server from time spoofing. This occurs when an attacker tries to feed incorrect time data into the system. Backing up the NTP server's configurations is standard procedure, so in the event of any issues, the system can be restored promptly. A review of IP address allocation and management using DHCP. You've learned that an IP address is a unique identifier for devices in a network. Much like each home needs a specific address for correct mail delivery, every device within a network requires an IP address to facilitate the correct routing of data. You also learned that devices can receive IP addresses using DHCP. DHCP servers play a vital role in this process, automating the allocation and management of IP addresses. Let's review DHCP as a network service. Function of DHCP. The primary function of DHCP servers is to streamline the assignment of IP addresses within a network, ensuring that each device receives a unique identifier. By doing so, DHCP eliminates the need for manual intervention by network administrators, thereby reducing the likelihood of errors such as IP address conflicts. Mechanism of DHCP. Upon connecting to a network, a device initiates a request for an IP address. DHCP servers take this request and assign an available address from a predefined pool, granting the device a lease on that IP address for a specified duration. When the lease duration approaches its end, the device can either renew its existing IP address or request a new one from DHCP. This process is largely transparent to the user. Significance of DHCP. The automation provided by DHCP is indispensable in contemporary network management. Without DHCP, the task of manually assigning unique IP addresses to each device on a network falls upon network administrators. This manual process is not only labor-intensive but also prone to errors, such as the accidental allocation of the same IP address to multiple devices. DHCP mitigates these challenges by automatically allocating, renewing, and recycling IP addresses. Limitations and considerations. While DHCP serves a critical role in most network settings, there are scenarios where it might not be the most suitable option. For example, servers often require static IP addresses that remain constant over time for reliable data routing. In such instances, DHCP can be configured to assign a permanent IP address to specific devices, thus ensuring consistency. DHCP servers are instrumental in the modern network architecture for automating the complex task of IP address allocation and management. Its capability to efficiently assign, renew, and manage IP addresses minimizes administrative burden and error, thus optimizing network performance and reliability. Troubleshooting and maintaining DHCP. Finding, fixing, and preventing problems with DHCP are tasks that the IT support professional is responsible for. When a device struggles to connect to the network, one of the first things the technician checks is whether it has been correctly assigned an IP address by the DHCP server. If there's an issue, the technician might release the current IP address and request a new one for that device. This is like switching a guest's room in a hotel. They also ensure that the pool of available IP addresses is sufficient, and that no two devices get assigned the same address, preventing conflicts. Continuous maintenance and vigilance are important for flawless DHCP operation. IT support technicians regularly monitor the DHCP server to ensure it operates efficiently and securely. They also keep an eye out for any unauthorized DHCP servers that might pop up on the network, which could potentially disrupt the normal flow of IP address assignments. Regular backups of the DHCP server's configuration data are a standard practice, ensuring that in the event of any malfunction, the system can be swiftly reinstated. Next, you'll explore how each of these network services DHCP, DSN, and NTP work together on a network. Interaction of DHCP, DNS, and NTP on a network. To understand how all these protocols work together on a network, imagine a laptop that uses each of these protocols to help a person get their work done in a day. The laptop connects to a personal LAN and the internet to do various jobs. Let's follow how the protocols enable the laptop to get the work done. Meet Lanny. In the cozy confines of a suburban home office, lives Lanny the laptop. Every morning, Lanny wakes up from sleep mode, eager to connect to the world and assist its user, Mikala, with her daily tasks. Lanny has a group of invisible helpers DHCP, DNS, and NTP that enable it to communicate efficiently on the network. An illustration of a personified laptop smiling. The morning routine, DHCP helps Lanny find a home. As Lanny wakes, it begins seeking an IP address to join the home network. This is where DHCP helps. With a quick, "Good morning, DHCP. May I have an IP address?" Lanny is assigned a unique IP address that allows it to be recognized on the network. An illustration of a personified laptop asking a question. Midday catch-up, DNS makes sense of web addresses. After obtaining its IP address, Lanny is ready for Mikala to browse the web, check emails, stream videos, and start her workday. When Mikala types in a website name, such as www.ibm.com, Lanny reaches out to DNS. DNS takes the website name and translates it into an IP address so Lanny can find the host server and load the website Mikala is requesting. For example, when Mikala wants to watch a training video, Lanny asks DNS, "Where can I find www.videowebsite.com?" DNS replies, "You can find it at IP address such and such," guiding Lanny to the right place on the web. An illustration of a personified laptop with a web address on the screen. Keeping time, NTP ensures Lanny is punctual. During these activities, it's important for Lanny to keep accurate time. Network Time Protocol, or NTP, serves as Lanny's personal watch, syncing its internal clock with a more accurate, universal time. Whenever Lanny feels like it's losing track of time, it syncs with NTP to ensure it's always punctual. Illustration of a personified laptop displaying a clock. Evening wrap-up, how it all comes together. As the day comes to an end, Lanny prepares for sleep mode. Before nodding off, it reflects on how DHCP, DNS, and NTP work together to keep it functional. DHCP helps it establish a presence on the network by providing an IP address. DNS translates human-friendly names into addresses that Lanny can understand. NTP makes sure Lanny operates on accurate time for all its tasks and appointments. These protocols, though invisible to Mikala, play a crucial role in Lanny's ability to serve Mikala as she works and stay connected to the world. As it closes its circuits for the night, Lanny is grateful for these unsung heroes, knowing that they will be there to assist it as soon as it wakes up the next day. Lanny goes into sleep mode, connected and ready to face another day of digital adventures. An illustration of a personified laptop sleeping. Summary and looking ahead. In this lesson, you learned about several systems and protocols that make the Internet function. You learned about NTP for time synchronization, DNS for resolving IP addresses, and DHCP for automated IP address allocation. You explored how these protocols work together and their roles in network operations. You've completed the final lesson of this module. Next, you'll review the module's key points and explore additional resources related to network protocols, technologies, and IP addresses. Points to remember. Key concepts. 1. Ports act as designated gates to direct different types of network traffic to the correct destination. 2. Protocols define the rules and procedures for communication between devices on a network. 3. Services are specialized software programs that perform specific functions on a network. 4. LAN protocols, such as Ethernet, are designed for quick, reliable data transfer over short distances. 5. WAN protocols, such as MPLS, are equipped for long-distance routing, data rate adaptability, and error correction. 6. Internet protocols, such as TCP/IP, HTTP, HTTPS, and FTP, work across both LANs and WANs to transfer data. 7. IP addressing, DHCP, and IP reservations ensure devices be identified and located on a network. 8. Encapsulation and multiplexing facilitate data transmission over complex WANs. 9. DNS is a directory technology that matches domain names with IP addresses so sites can be located without memorizing numbers. 10. Common LAN technologies, such as Ethernet, Token Ring, and FDDI, have different network topologies and speeds. 11. Internet protocols, such as SIP, RTP, SMPP, and XMPP, enable different forms of communication over the Internet. 12. Email protocols, such as SMTP, POP3, and IMAP, facilitate sending, receiving, and managing email messages. 13. Network optimization techniques, such as traffic shaping, quality of service, and fast rerouting, improve performance. 14. NTP, DHCP, and DNS services work together to connect devices, assign addresses, resolve names, and synchronize time. Big ideas. In addition, you explored or practiced these skills. Employability skills. Critical thinking. Organize steps for accessing a secure website using HTTPS. Apply knowledge of network protocols to a scenario. Explain how data moves through a network using ports, protocols, and services. Collaboration and teaming. Assist a senior IT support technician in a scenario to apply knowledge of network services to configure and manage IP addressing. Problem solving. Troubleshoot a network using IP addressing. Determine the cause of problems with network connectivity. Describe ways to optimize WAN networks for optimal performance. Learning objectives. Now that you've completed this module, you should be able to explain the role of ports, protocols, and services and their process of working together in network communication. Explain the purpose and functions of Internet protocols. Describe the characteristics and application of LAN technologies. Follow the process for configuring and managing IP addressing. Describe the characteristics and application of WAN technologies. Choose a common optimization technique for a WAN technology given a scenario. Describe Internet protocols that power Internet-based communication tools and email. Analyze methods to troubleshoot Internet communication tools and Internet protocols given a scenario. Explain the role of different network services that support the functionality of the Internet. Determine the network service to troubleshoot given a scenario. Explore more resources. To explore concepts covered in this module in more depth, check out these resources. Network ports and protocols CompTIA Network Plus N10-0071.1, opens in a new tab. In this video, TechG from Technology G explains the purpose and uses of various networking ports and protocols. The fundamentals of an Ethernet LAN, explained, opens in a new tab. This blog by Nadeem Anuth for LifeWire explains how and why Ethernet is the technology that is commonly used in wired local area networks. Connecting all the things in the Internet of Things, opens in a new tab. This article from IBM Developer provides a guide to selecting network technologies to solve IoT challenges. How IP addresses work. Network Fundamentals Part 4, opens in a new tab. This video from Network Direction in the Network Foundation series explains IP addressing and how it works.